Okay, good. So let's see actually what it is. So all of us will come to know. So exactly, it's a programmable logic device configured after manufacturing. That's exactly the fundamental differences. So there are, it's like a, today we have got a lot of automation devices over there. So this fabric chip, when it was designed in such a manner that it can remain be programmable and it can be mass manufactured, so many people can actually use it. Wonderful. So thank you so much for your response. So let's actually find out what exactly the FPGA technologies. So FPGA technology, if you really look at it, so is a field programmable gate array is an integrated circuit that is configured by the user as applicable, okay, as per your application. So it means that somebody has come up with a novel idea that also in 80s, if you really go back to the history of that, so that they can create a functional logic block, what once upon a time what we used to do as a programmable, a small on the breadboard designs. And that's where the whole evolution started of field programmable gate arrays. And there are multiples, we'll look at it. So FPGA, allows designers to test and validate custom hardware designs before committing to full-scale fabrication of ASIC. That was a fundamental motivation for people to innovate FPGAs so that people can actually go ASIC route, because ASIC design and fabrication in 80s, it was so expensive and it is used to take so much of a time, even till today also, if for a chip wafer fabrication to go that, it takes 6 months, even if in today's time. So you can imagine right from the design till manufacturing how long the time was involved. So that's why people went for a programmable devices. So there are many FPGA architectures, and architecture has got actually array of logic block. Ultimately, we all know that the entire digital system design is based on flip-flops, AND gate, NAND gate, OR gates, and a combination of that creates your entire digital design. And at the end of that, you still need interconnect IO blocks, that's the wiring, and then physical device or the universal world which needs to interface, you need certain kind of devices. And then there are technologies available outside to that, which we know that USB or UART, CAN bus, Modbus, there are so many peripheral connectivity what we need it. So all that as an architecture, it should be able to provide it. So the flexibility that FPGA allows for custom design from a simple control unit to very complex application is a FPGA technology. So in today, who are FPGA market leaders if you look at it? So Xilinx is one of the company which many of you might have known and used or heard about it, which is acquired by AMD now, is a market leader in FPGA and for high performance devices, and it range is huge. And their latest series is Versal and the Vertex series, and Vertex series date back in 99 2000, which I have used personally. Then there is the Intel or Altera. So Xilinx and Altera were that, so Intel purchased it. So consolidation of the industry taking place. Then Lattice Semiconductor is also known for very low power FPGAs, which are used in the in-circuit emulators and the programming series, and their ICE and the ECP series, they are ultra low power. So where you want to save a lot of power, because FPGA consumes a lot of power, Lattice Semiconductors devices are there. Then Microchip Technology also offers Microsemi brand their FPGAs for aerospace, defense, industrial applications, and they are known for their reliability which is needed in such kind of application. And then there is a little heard known name by most of the people in India is Arconix. They specialize in really high performance, high bandwidth FPGA, which are actually using for as machine learning, network accelerations, then your cloud computing, your servers, and they are very specialized people. So common people won't go for Arconics as a device as in terms of Xilinx or Intel. So that's a market space, just to give you an idea about it. So when we are talking about a programmable logic resource, and I talked about fundamental gates. So ultimately, each one of us know today, when we developed a semiconductor chip, finally it boils down to a final transistor, which yesterday Mr. Vinay Sharma very nicely actually demonstrated you how it is built right from the scratch using a tool. Now taking that as a base, then we go to the gates level, we go to the IP level, we go to the multiple blocks and reuse all those components over and over again and again, because we don't want to do the same thing fundamentally. So the transistor and its technology remains at the core. The rest of the logics which has been built over a period of time, they get transition. So it's an integral block gets into the gates as the resources. And in order to create a programmable, your custom design, what you need is a programmable resources. Meaning the functionality of AND gate, NAND gate, NOR gate, everything, they need to be built inside your field programmable gate arrays. So how it is done? That is done through called as a logic building blocks, which are the programmable logic building blocks. I didn't know that so many of you are absolutely brand new to the FPGA as such, but just to give you a nutshell and idea, primary for every gate, you ultimately have a truth table based on the number of inputs. So if the number of inputs are 2, then you get 4 combinations of that, 0, 0, 0, 1, 1, 0 and all that. So if the number of input increases to 3, then it becomes 2 raised to power of 3, 2 raised to power of 4, 16, right? So you go into the multiples of the order of 2, 4, 8, 16, 32, 64. So naturally the combination will keep increasing and you will start getting actually the desired output as 1 point. So ultimately it's basically a kind of a lookup table where number of inputs will come and you get output. So this logic building block is defined as a variable resource in a FPGA. And Xilinx and Intel offered this FPGA with various of a gate counts. Because today, with a multiple gate counts combined together, you will form a certain logic which can be a programmable one. So when we are using a single transistor and the gates, naturally the utilization is 100%. That is, you will be utilizing each and each device to its fullest. But when we are creating a programmable or general purpose things, we'll have to take into account some kind of a wastage. So that's why the gate count, it will change across vendor depending on their architecture. And what exactly happens with the gate count? Gate count will impact directly ability to how much you can implement your complex logic. So naturally, like a Moore's law, the FPGA technology also enhanced over a period of time. So how much different logic what you can put, how many number of gates what you can put in there in a flexible manner, what kind of different hard logic building blocks you can actually implement into that. All that dominated the entire market for last 4 decades. And that's why the programmable resource as a FPGA becoming very a unique feature, and it's not easy to understand usage also and get a mastery of that over a period of time. So let's take actually a small another one. So which FPGA resources are most commonly used for building your actually digital blocks? So this combination will actually tell you what are those. So these are the 4 options. If you really look at this, so Please use your chat box and see what can the answer you can come up with out of the 4 options. So some of you are saying B, C, D, C, okay. Good. So let's actually see what the answer is. Yes. Just now what I talked about it, using a lookup tables and the flip-flops associated with that, it creates a most flexible one. Yes, you definitely need memory blocks, you need soft IPs, you need NAND flash blocks as well, but combination of all of those, just a minute, are you getting disturbed? So let's move forward, go to the next slide. So we talked about the logic building blocks and how they can actually go and build your logic over there. So let's look at actually the available peripherals today in the FPGA. The available peripherals in the FPGA building blocks are USB interface, PCI interface, UART, and there is actually soft versus hard IP. So soft IP says it refers to a core that you can synthesize from your RTL code and offer a flexibility of putting it into the required logical block under the FPGA. While a hard IP is pre-configured or a design building block which is like an SoC or a semiconductor device and directly embedded into the chip where you can utilize it. And as of today with the 2026, because the semiconductor technology has moved from a SoC point of view to the multi-chip SoC as chiplet designs where multiple chips are put together, they are able to create FPGAs of much complex nature where you can have flexible IP, you can have hard SoCs there and also peripheral devices all combined together under one small chip. And this will keep on improving over a period of time. So what you will see in future, more complex FPGA building devices. So let's try to understand what exactly the design tool chain for FPGAs. I am not going into the detail of each building block of the FPGA because that's not actually I intend to, because I wanted to show you what exactly the overall idea of using FPGA as a design, and in your respective classes then you can actually go and teach into the detail. Many of your colleges might have C2S tool, however many colleges might be using generic tools, so we'll just look at it. So there are various tools available. So primarily what you need is a design entry tool. That's the starting point, because what you are trying to do, you are trying to enter your design which could be in a VHDL or Verilog format, or it could be in a schematic format. In any particular format, your thought process which you are designed needs to get entered into your tool. So that's where the design entry tool will come. The next one, as in the tool, comes as a synthesis level. So in the entire semiconductor terminology, what we call as actually the compilation process, in the compilation process is typically called as a synthesis process, because it's not just converting a software into some kind of a logical instruction, it is a synthesizing your higher level language into a executable gate level physical hardware, and that's why the terminology came as a synthesis. So it's not actually 1:1 translation of that, and that is the reason it is a synthesis process. and there are tools specifically for that. It take multiple stages. It will first check syntax, it will check uh, errors in the whole thing, it will convert it into the intermediate one like a compilation, because it has to understand it. Then it will synthesize it, your building blocks, into the various logic. Then the logic will put together. That entire tool chain will get covered into a final output such as called as a netlist. That is, which is says that these are the building blocks. If you connect the building blocks in terms of AND gate and NAND gates, not in terms of the instruction code of a software, it will perform as an hardware. That's why it's called as a synthesis. And then next comes as a phase as a place and route, because now it is a software wise, it is available to you how the design will look like in a tool, but then it needs to get placed onto a physical device on FPGA, and that's why the place and route mechanism, depending on the architecture of the FPGA, it will put resources on that, and it will show you where exactly the planning needs to be done. And the critical point in the whole thing becomes the timing analysis and optimization. Why? Because when you are designing the complex digital designs, the critical point is the entire, at that particular clock speed, your entire design has to work seamlessly. So you need to do your understanding of the design, whatever is being synthesized. It is not like you are drawing it with hand and taking care of it. The tool's understanding, you need to validate it well, and that's the reason it needs to be done. So let's take another kind of a quiz over there. The timing closure means what? And through this particular poll, what I understand over here, will come to know what your understanding is. Good. Some of you are saying C and some of you are saying D. Yes, yes. The partially both the answers would actually be going, because you wanted to see that the design fits into the whole thing. But what we are talking about here is the timing closure, whether it is meeting that particular one, and the last answer of the D is a proper one. So let's see the answer. What it says is your D. The design should meet all timing constraints of a target clock. What happens when you are designing at say 50 megahertz, 100 megahertz, which is internally clocked at a gigahertz speed, then you need to fit all your parameters of the digital circuit very well. And then you are designing it within 1 clock cycle, 2 clock cycle, or 10 clock cycle, depending on your design. So what you need to understand that your entire end-to-end design, from input to the output, fits into that entire timing block. And that's why the timing closure is an important aspect in semiconductor design, and so be it in a FPGA design. In a physical SoC also you need to do this, depending on the architecture of the technology in which you will be manufacturing it. Here, FPGA design, the technology and manufacturing you already selected. That's why it is pertaining to that particular device. You need to understand how the timing closures will be done. So it is also important to understand, are there any open source FPGA design tools available in the market today? Some of you might be aware of that, but like any other software industry, the semiconductor industry is also very, very open about using the open source design tools. So for RTS simulation, Veriliter is one, Verilog simulators are there. In order to waveform and understanding is GTK Wave is there. Synthesis on some particular devices meaning if you do a synthesis of that, your code has to fit to a target one on some technology, right? Yesterday you saw some tool which is very specific nature. Now if you want to incorporate a technology on which mapping needs to be done, then it needs to get supported on that. So that's another one. Then there would be requirement of references design. So how much reference design is available to you? Are there any processor available? So people are creating this, and the hands-on learning low cost FPGA development board, like your boards which is available, your Arduino boards, your ESP32 boards, the entire ecosystem what you are using it today for your IoT, something similar people are working on open source since many years. Only challenge of this is that they are still open source, and it is nobody takes actually the care that it can be actually industry ready, or industry you can use that particular tool to create a product which will fit in the market. And that's why for IP validation and typical your lab use or the college use, it is possible to use this tool. However, for a commercial application, it is not possible to use that. So there what you need is an optimization technique in FPGAs. So primarily what you need, FPGA has got a finite number of logic blocks, that's what we have seen. Or it might have actually the DSP cores inside. It will have memory block. Why you need a memory block? Because you need to store some particular data. You need to create some kind of a 5-hole. So generic resources which are available today, it has got a finite number. Because ultimately, how much a generic block you can fit into a general fabric is, I didn't know that there are so many people are just new to this. Otherwise, I would have shown you a generic building block of that. But you can imagine that you have got a basic building block puzzles, and because you wanted to interconnect them the way you like it, you will have limited choice. Versus if you have got a fixed resource where you can have your choice of putting it the way you want, you can get multiple options. So FPGA got a limited one. So resource utilization, how to do that, optimization technique is very important. So you need to learn those. How exactly the extract the capability of your FPGA to the fullest. And when you see a kind of a design as a case study, I'll show you what we could do it there. Then power optimization, because power consumption is a critical in any application, right? So when you are using these FPGA devices, then you need to use such that are they actually getting your clocks, because the clock frequency will create more power dissipation, your dynamic voltage swing will be there, your IO operations will be there. So which particular blocks are actually operating, which blocks are not operating, all that needs to be taken into account. And overall performance tuning is really important, because you wanted to understand at what speed your design is running. Your designing may use a parallelism or pipelining. For example, there could be multiple building blocks, they could work in a parallel. Within that particular block, there could be multiple pipelines. It may not happen in one clock cycle. It might need couple of clock cycles. And all that performance tuning has to be done to meet your final one. And it's a very complex one. It's not an easy task. There is another call, because as I said, there are multiple building blocks, parallelism. So there is another issue keeps coming over there as a clock domain crossing issues. It happens over there. So these are the options. Let's see whether you are aware of such kind of thing. CDC means clock domain crossing. I don't know how many of you are aware. I'll explain you in nutshell how the things happen in a digital design, why it is important. But primarily, this is the biggest challenge in semiconductor design, be it on FPGA or be it on a SoC design. So I don't know what kind of answers are coming over there. D, okay. E. Fine. So let's take a look at what exactly so if you really look at the CDCB's clock domain crossing will, what happens, there are two building blocks which are crossing from operating at a different frequency. This is a challenge what will happen. Signal crosses between a different clock domains without proper synchronization. And I'll give you some example of this. In the next slide, you will come to know. This is a example slide what I would like to show it to you. So what they are showing over here is there is a clock domain A, there is a clock domain B. Say one side of the clock is say maybe 10 megahertz, 15 megahertz input coming at one side. You are processing at the clock which is at a higher speed. And they are not necessarily that they are actually in a sync pair. So what will happen? The input clock which is clocking the flip-flop at this end as input at clock A, when the output comes which is available for the building block or the 2, it might just not see that edge because the two clocks might be close to each other. It will be might happen exactly at the same time, and metastability issue might come. So what happens the metastability? When signal actually come in a domain, sometimes you see them, sometimes you don't see that. What actually happens in a real life scenario? If the two instances happen exactly at the same time, there is a good chances that you will see a previous or the next new state, right? The same thing will happen in a digital design. And how it is taken care? So there are methodologies which are fixed and which is proven for years. So if there is a flip-flop which is clocking at the clock age, then you put two flip-flops in sync, where you first click it at the sync one. So sometimes it sees or sometimes it doesn't see. And then in the next clock cycle, the output of one is given to the sync of the two. So final output over here will always be in the synchronization. So what you need is in one extra clock edge. But whenever your design is actually using from sync 2, it is always a properly captured signal. It might happen that the one clock cycle is wasted over here. You might not see that particular clock cycle in some design. So at the output of the B here, which is a stable output, you will say ultimately it's an event which is coming at that point of time. So it will work. Or it could be a bus, for example. This is a 32-bit bus or 64-bit bus coming from a process A and crossing domain to the process 2. Like asynchronous, there are two remote building blocks and they are crossing the boundaries. What will happen? You just cannot use actually practically a single clock cycle to just capture it over there. So what you need at that point of time is called as a first in first out of FIFO, which I'm sure you must have learnt in your curriculum or previously as well. So primarily on left hand side you put your data which is here at one clock edge and the output taken at the different clock edge which is a clock B. Both are just mapping this entire FIFO buffer so that there is the input and there is output. And once this happens, then the entire bus output can be in a synchronous. What you are seeing is whichever is putting into the FIFO that will go out. Otherwise, what will happen? You will need such a synchronization flops for all of them and they may not actually happen at the same time. That is a challenge, right? Because for a single bit it is okay. But you can imagine the 32 bits, even if at the sync 2 level, some of them can happen at the 0th clock, some of them can happen at the next clock. And all such kind of instances, if it is happening, your design will never work. So one has to understand all this in the design domain. Okay. So let's try to understand as to why exactly you are trying to do this prototyping and why it is necessary. I'm just doing a time check as well. So why this prototyping is really necessary? As we said, a FPGA allows for designers to quickly test your ASICs, right? And that's why it's called as a rapid prototyping. Otherwise, everybody will have to make a design, fabricate a chip, and then see whether the chip is working or not working. And that is not possible. Of course, there are designs in the world which just cannot fit into the FPGA and you have to develop SoC for that. Or the people, those who have seasoned, those who know the FPGA resources are of no use and the design can be taken to the SoC level, they will spend all that experience and do only the final one. But most of the people will first go for emulation technology, SOC validation, which will take multiple teams, multiple months, multiple years of actually combined efforts over there. Then there is a reusability is there. Design which we have used can be modified and reiterated number of times. So iterations are important. There are certain changes which actually happens in a technology and which we faced, and I'll show you how we catered to all of those. Then system verification. FPGA to be used to verify functionality of a system before actual hardware is available. Many times the systems are designed in advance, there nothing is actually available, and then you need to create certain things. How one does? Imagine a case of a USB. When the USB technology was evolved around 92, 93, and then later on it was of very slow speed, 1 megabit per second. Then it went to actually 10 to 12 and then 100 mega. Okay, that is high speed bus, and now it is much more. In those days, even the PC till 2000, there was no port available, or 98, 99 till that time. Only your low speed port, LS speed, was available. There was no your previously mouse which was actually there, it was not available on your USB. So how people designed it? In fact, you can imagine how we designed it. In fact, we designed USB tools which I'll show you later. But then that time there was no software, there is no device driver, there is no USB stick, nothing was there. But then we were designing all of those ahead of time. So we had to make use of verification methodology using FPGAs, and we used it very effectively in 90s to create those functional blocks. And then hardware software integration. Like exactly I told you, you create a USB or maybe IEEE 1394 or UART, CAN bus, all such kind of interfaces, but then you need a software for that. You need a device driver, you need operating system to understand it. So when it will actually happen? You will make a chip which will take 2-3 years, then you start writing software, then you build it. When the things will actually happen in industry? Time to market is absolutely critical. That's why such kind of a prototyping methodologies are very, very popular and useful. So let's try to understand what are the main reasons that it can be used. Again, try to answer it. It is based on the previous one. What I am just showing you, so that you are, whatever we are discussing so far, it just get robust in your mind. Okay. So what do you think? Very good. Thanks for actually responding it. Almost all are saying actually A. But is it really true? Yes. It enables faster hardware execution and real I/O testing than simulation. That is what we have seen in the previous slides. Why do we need to do that? Simulation will take ages. And actually what you need to do is a quick prototype, and that's the reason why we should be doing it. So how do one select actually the FPGA for your validation? Well, what type of actually the FPGA you will select for it? I know it is going to be very, very difficult for you to understand this aspect over there, because ultimately you need to understand and size your design. So capacity, whether it has got a VRAM blocks or URAM blocks or high bandwidth memory blocks, logic blocks, flip-flops, how many LUTs, logical user lookup tables, okay, how much your design can fit into that, which particular building block will take how many resources, how to estimate it. So that's why it depends on that. What type of the interfaces you are going to use in your entire system, whether you need an Ethernet interface, whether you need a DDR memory interface, you need a PCI Express or older interfaces, whether you need a serial and deserialization, which is called as the SerDes, which is works at gigabit speeds. Do you need that? Do you need to connect it to the real world? What type of the frequency you wanted to achieve? Because the frequency max which can be achieved is a design dependent. Routing, utilization, what the kind of architecture what you're going to implement it, and the physical challenges which can happen into that. Then how you are going to actually debug and see the visibility inside a chip. That's another big problem when you are designing a semiconductor. Whatever you are designed, how you are going to say, for example, if you create a breadboard design, then you can put your oscilloscope everywhere. But how do you do actually the testing of such kind of this thing? Is very, very complex. Anything could go wrong at any point of time. You may be able to see it in simulation, but how to do that visibility in real FPGA is a big challenge, and that's not easy. It takes actually months and days to understand. You need to implement various methodologies over there. So there are big challenges there. And then the tool chain maturity. Whether the tool chain is appropriate for that, whether the Intel is a better one, or the microchip is better, or Arconix is better, or Xilinx is better. What are the constraints, what they can do, what they cannot do, whether these are actually supported in the ecosystem, are people using it and actually utilize it very effectively. So all that is very, very important to understand it. So this is just a comparison chart for the vendor clock speeds and the dipper. Practically at as a clock speed basis, you won't get as a 1.5 gigahertz as a external clock which is coming in. The external clock which is given to that is always low, but internal to the fabrics, you can clock multiply it to the higher rate, and that's why it is written as 1.5 gigs. Externally it will work only at maybe 200 megahertz, 500 megahertz, and then you implement actually the PLLs inside and synthesize the higher frequency clock, which is typically at a very low or maybe kind of a restricted usage area. So then so you can get 10 million gate counts, 9 million, 500k gate counts. Then it supports actually USB. Yes, it can support in some of them in a hard way. That is, for example, microchip says, I will give you USB building block directly. You don't have to do anything. Here they will say that soft IP, which we'll see slowly in the next slides. Then it gives hard IP. And then whether what type of the SPI, I2C, what you see in your microcontrollers, are they available? Which particular tool chain is available? What is the power consumption? And what kind of actually the ecosystem is available? It may that soft intellectual properties and the hard intellectual property. How they are available, that one has to actually see. So FPGA technologies currently in the manufacturing is actually at the 7 nanometer level as well. And yesterday we have seen what does the 2 nanometer mean, 7 nanometer mean in terms of the FinFET transistors, in terms of the structure. And in fact, I was actually attending like what you people are attending it today. I was equally curious to know, and it was a fantastic explanation. So why exactly when we say 2 nanometer, whether it's really 2 nanometer to the channel length or it's something different. And so these various technologies, what it evolved, let's not go into the transistor level over there, but let's focus it onto the, but you get actually from the highest technology node today available, Xilinx, everybody is producing that because there is a competition to that. FPGAs are used in very high-end applications, and that's the reason the technology has gone way ahead, and you can use actually fast design, ultra low power. All these FPGAs are actually available today in manufacturing. So you get a wide variety of, they are pretty expensive, but there is a wide variety of things which is available to us. What are the future trends in actually FPGA technologies? So FPGA technology is evolving technology. What I used 20 years before and today what actually is available to use way different. Architectures are same, but the complexities, the IP available, the tool chain available, the more and more sophistication has gone. And with the advantage of actually the AI technology, it is getting a popularity in terms of the designing itself, using the AI based tool, using your algorithms. You can fit your AI algorithms onto the FPGAs, or they are creating a building blocks which can directly fit onto the FPGAs as well. So all the new technologies what you see available today in the SoCs, the people are trying to put a small part of that into the FPGA, and this will keep on evolving, because FPGA vendor would see this as an opportunity to go to the market pretty quickly, and people will keep consuming it. So AI and machine learning is focusing is large. So for FPGA being used in AI model in inferences and training acceleration, because this is the most important thing which actually happens. Then your edge computing, for example, lattice I told you, it takes 1 or 2 watts. Cool runner CPLDs from a Xilinx actually takes few couple of actually watts instead of actually the high wattages. So few hundred milliwatts you can consume it, and you can write your various devices design in an edge computing mode for IoT. So all that is actually possible using the FPGA. So trends are actually ever increasing. So as a recap for this, we say is a flexibility, performance and cost effectiveness is an important aspect for madam. I would like to just do a time check. In fact, we started late, I know that, but the next speaker might be available at 7:30, right? So I can skip couple of them.
Yeah, sir.
So what do you recommend? Because there might be for a next speaker, he might get delayed, which we can avoid it, right?
Yes, I'll just confirm over the speaker. Please, you
Okay.
continue. I'll just inform you.
Okay, fine. Yeah. Thank you so much. Yeah. So this is the basic thing what you need to do as a consideration. So let's actually look at actually some kind of an introduction to IP cores and implementation of FPG, because this is an important thing why we are actually looking at this particular aspect of designing it. So FPGA, when you are seeing it, how the IP core. Last time we talked about IP core, which are called as the intellectual property core, is nothing but your logic building block which you are designed for your specific application, be it a microcontroller, be it a USB, be it any peripheral device, be it your proprietary design which you wanted to fit into the entire as a synthesizable SoC. All that is your intellectual property core, and that's why it is called as a pre-designed, pre-verified blocks of a logic or function block that can be integrated into the RTL designs. And when you are saying that IP you are actually giving, it means that it should be available to as a user and they can utilize it. Like what you do a custom build, when you build a product, that product you manufacture in multiples and actually give it to multiple people. The same way, your intellectual property code of your logic building block, you should be able to hand it over to the multiple peoples and they should be able to use it effectively. And that is what we are going to see. If you need to do that, how to achieve it, because saying is simpler but achieving is extremely difficult. And so for example, when you are using a microprocessor today, you see 100 and 200 pages of documentation and you go through each part of that. You utilize it and make it a generic your code. You write software on that and you create the same microcontroller uses in hundreds of different applications. Now imagine the same way, whatever the building block you are designed, maybe millions of people wanted to use that. So how that can be created and how that can be tested in SoC or in FPGA. So the purpose is very known. So all the commonly used a block like a subroutine or subfunction, what you are being commonly doing it in software, how that can be same thing can be implemented in this thing. How it can be configurable is another this symbol. So it will reduce a time to market, it will save somebody's money, time, and whatever that he saves it, he will be able to offer that as a service to somebody else. He say, okay, I am saving you millions of dollars without investing in the same thing. You utilize it and you pay me maybe 1/10 of that, and I get 1/10 from thousands of them, and I make money out of that. That's why people are going for intellectual property. And all people really should look at how they can create their own intellectual properties. So there are two types of the intellectual properties in the terms of the semiconductor. So what are those types? They are called as the soft IP cores. Basically, core is nothing but your design, RTL design. So the description is, it is delivered as a RTL code itself, like a software library. You just give it to them, and that software library, then you can customize it. Say for example, you give your parameters to that and say that the address bus and the data bus can be 32-bit wide, 16-bit wide. Output can be, instead of 1, it can be hundreds, 5, and your entire logic internally will become that big. It's exactly like a software. Now where exactly the challenge will come? When that software which you have given it to someone, when it needs to get implemented, implementation will keep on changing. Unlike in software, when you are developing a subroutine and executing in a CPU or your PC, nothing changes much. It would actually give you expansion in terms of loop counts, but it is all software. You might need more number of clock cycles, more number of memory if you say buffer size is increased. You can imagine the same resources which is available in a software getting utilized in a same PC, right? But imagine the same thing happening on a hardware. All of a sudden, instead of actually 16-bit bus, you wanted a 64-bit bus. It means that practically physical path has to be carved out, and that's the reason the challenges comes over there in designing all this. And there are another code is called hardcore IPs, meaning literally a microcontroller or Arduino core, Arduino IC. If you are putting that Arduino core IC directly on the FPGA and giving it to you as a combined one, saying that the Arduino code is already inside and all the lines are actually already connected to you as a board. What you do, you write rest of the portion and use Arduino as it is. You will say that, oh, I don't have to do actually much now. Whatever I used to do in my Arduino, the same thing will work there. And that is the advantage of hardware IPs. So it reduces that particular, because you no longer synthesize it and try to fit again in a different building blocks. So you save a lot of energy and resources also you save, because it is not a generic one, it is a fixed one. So soft IP and the hard IP cores, and all vendors they provide both. Sometimes you need a hardcore IP, sometimes you need a soft IP, and depending on the application both are useful. For example, USB, nowadays USB is so known, you know that what exactly the function it does. You need a software flexibility, you don't need a hardware flexibility. So that's a UART. You don't need actually the software, the hardware is a flexible over there. Fixed 8-bit 10-bit, so that code can be fixed. You don't have to worry about it. It's utilization, you can do it in a different way. Similarly, your I2C, SPI, they are the fixed building blocks, and those can be actually hard coded as a SoC or the system chip itself onto the FPGA. So let's see actually what the soft IP typically means. So it's a recap, understanding is, right? So there are 4 options. Just see, understand which one are actually appropriate. In meanwhile, actually I am seeing a code also. Yeah, okay. I'll take this one as well. Okay. So let's see the answer of this. So are you typing here which one? E. Right. So let's look at as the answer over here. Yes. A synthesizable RTL that can be customized and mapped to an FPGA. That's exactly I said in the previous explanation. So meanwhile, somebody has asked a question over there saying that how one chooses as a nanometer technology. Hello. 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 Can somebody mute them?
Yes, sir. I have muted the participants. You can continue, sir. Hello. Sir, you are not audible.
Oh, you have muted me also. Thank you so much. Okay. Yeah. So primarily what has happened, when you select a technology, you don't go by 7 nanometer or something. Don't look at that as a technology. What you need to do, these technologies are available as a, so when you choose a technology of a FPGA, parameters what I have given you, its number of clock cycles, number of blocks, IP core, how much logic it can fit. As actually number of gates will increase, automatically the technology will keep on shrinking. So don't have to worry about which nanometer technology you wanted to use. It's like a CPU or GPU. You don't worry about whether it is a 6 nanometer or 7 nanometer. However, when you are designing a semiconductor, that time you need to see which technology you will be using it, not in the FPGA or IP core design. In a semiconductor design, you need to look at it because it's very important to see at what technology node you want to develop at that speed, clock speed, everything together. Right now you are using a technology which is already designed it over there. Okay. Okay. So why it is important to actually consider it, IP core is the time to market reduction, cost efficiency, reliability and the proven quality. That's why the IP cores are very popular. I don't do today same IP core again and again. I don't want to actually reinvent the whole wheel again, right? The cost efficiency I can take care of it. I can reuse your IP cores even if at my end. It's like a company provides certain building blocks and people can utilize it multiple times. That's why it is important to do design an IP core in FPGA building blocks. So what are the IP core sources available? It can be in-house, it can be third party, it can be in FPGA vendor libraries itself. So for example, Xilinx will provide you their own libraries. They say, okay, we have done it enough, just you utilize it. You don't have to worry about it. While few people will say that, no. This is an IP which is available on any, for example, ARM, Synosys, Cadence. They say that this is the IP which can fit on this FPGAs. You utilize them. Why you will buy them? Because they are the very certified one and the very useful one. They do something specific efficiently. And sometimes you will develop it in-house because you will not be able to afford them. But then you have actually at your time, at your hand, and you can actually afford to do still a part of that. You do not need an entire ARM core, but you need a part of that. So depending on that, one will choose about it. So there are certain actually methodologies, and I will just go through that because there are really tons of slides over there. We cannot actually, as we started little late. So basically design flow and the tools, integration, how to do that. So you select it, you configure it, and you integrate and validate it. So when IP core, when you do that, what you need to do? FPGA tool chain is the same. There is no difference between that. So you will choose an design flow methodology, select IP from a specific vendor and put it in your core, and then you will start utilizing your HDL code in and around that and verify that entire logic building block. Then challenges will come in integration. If you are taking the IP from various vendors, then you need to be sure about it. It can be properly utilized. It is compatible. It is serving the purpose. Because it is a customizable one, it might not suit your specific need. Then there is the licensing cost. When somebody has done already something, they expect money to be earned on that, which you will also expect it. And the customization limitation. That's why people would go for a soft IP sometimes, because they can have a lot better customization possibilities than the hardcore IPs. And hardcore IPs are specific nature, because you don't need sometimes any changes over there, you will go for a hard IPs. So examples like UART, SPI, Ethernet, memory interfaces, they are all examples of the code. You don't have to worry about all this. This is being done for ages now. Okay, ADC, DAC, PCI, PCI Express, they are the standard buses, everything, many people have done that. If you want to do the same thing, you will spend 2-3 years easily in that, in validating, doing that. It's better to use directly the one which is available as a IP course, and you create your own new IP based on the top of that. Then step in developing that, you need to draw good specification, understand requirements, find out what is the generic thing what you would like to do. Are there any compliances to be met? So all that checklist has to be done. So that is how you will actually create it. Then you need to have clear good documentation of building block, outlining each and each actually specification of your building block, descriptions of signal, timing, any step what you will do in your design, RTL design. Then comes the stage of design, which is architecture design, RTL coding, design tools, same. So developing your higher level architecture and taking it to the entire coding cycle. So entire design team would be fitting on the top of that, and then you will do the designing of that. Then simulation, again RTL the same, flow is absolutely the same, flow is not getting changed, right? The flow is absolutely same. So you do simulation, you do test bench development, you create building blocks for each of them, combine all of them, and then do a functional simulation. Then you can use any particular tool. You can use Cadence tool, you can use Model Sim, Quattro Sim, or Simplicity. The number of tools, open source tool, any typical tool what you can use it as a one. Then the step what we see in the previous one as a synthesis. So RTL synthesis specific to the gate level of a target FPGA. That is what is really critical in this. Because why? Your IP will fit into a specific FPGA. Now if it needs to be fixed into the say 10 different type of the FPGA, what you will do? So what you have to do is you need to select the lower FPGA and the higher FPGA. It's like actually taking a different model of different operating system or different Samsung phones, iPhones, and see that your application runs everywhere. Exactly the same thing. You will take a target FPGA and put it across. If the architecture is same for the design, it will definitely fit. It might just fit in a one corner, or it might consume 10%, 20% or 100% depending on the size of that particular FPGA, right? Then what are the timing constraints available? Example, suppose your speed requirement is very high, then you will not be able to support a low speed FPGAs. So you will have to target them properly and utilize it. Then implementation methodology, place and route, implementation tools, Xilinx, Vivaldo, Intel Quartus, timing analysis, so that your entire RTL design flow remains the same. There is no difference. So let's actually take this as a small understanding. Steps involved in writing actually RTL to FPGA resources. What are the things? So whether it is a firmware compilation, writing, place and route, or synthesis only. For actual FPGA implementation, what you need here is place and route. Because every FPGA resources in the description is different. So your RTL is generic. Your synthesis is very specific to a specific target. And that's the reason it's like compiling to a specific microcontroller the same code. The same thing will happen as an analogy for your FPGAs. Then there is a debugging is a critical point in your this thing. How do you debug or how you verify, validate your FPGA based designs? What are the toolkits which is available? So there are certain protocol checkers, on-chip captures. So one has to build actually some kind of a tool which is built inside your RTL coding itself, which will give visibility. Is like you do a software debugging, what you do? You give actually some kind of a printf message, right? Now it is not possible to do printf message in FPGA building block. So what you will do? You will have to create some dummy block internally which will capture the signal and provide it to you outside world. And so there are some methodology which is developed on-chip capture. They are called as a ILA, that is your logic analyzers, internal logic analyzer, chip scope, signal trap, VIO, triggers and trace buffers. They are the methodology which is evolved over a period of time in FPGA validation. So these are nothing but the building blocks which you can incorporate. So this is a fixed block. When you incorporate it, it consumes certain area. But when your design is completely validated, you don't need them. And that's why the beauty of that is understanding which particular is like a multimeter. which you are putting it inside your FPGA, or oscilloscope which you are putting it internal to the FPGA, or writing a software building block internal to your FPGA. So these are the various methodologies one has to actually do. You might need an external analyzer as well, because if you are connecting it to the bus, USB, PCI Express, Ethernet, then you might need that. If you are using a Wi-Fi, you might need Wi-Fi analyzers. So FPGA based validation involves the entire ecosystem as well. So that's why I say verification, functional, formal, hardware testing. So these are the steps involved in actually developing the cores. I am sure actually this is a very simple thing. Which tool is used for internal signal capture inside FPGA? I already told you this. So yes, is a internal tool called internal logic analyzer or chip scope or signal track, and not like an Excel sheet or what you will put generally, or Wireshark or GitHub, where you can do using a software and put all of this. But as a hardware point of view, you need to do it something differently. So optimization is really required. So you need to do performance tuning, resource utilization, and all that method. So what I'll do, maybe I would like to actually skip few slides, which is packaging delivery is an important aspect. You'll have to core it, because why it is important? Your IP core is to be utilized by somebody else. So you need to create packaging properly. How your core will be given, how the code will be given, how the source file will be given. Is it a compiled code, netlist will be given, user guide, documentation, all that is really important. How will you support, how will you maintain it? How will you, if somebody says that there is a bug, how will you fix the bug? It's like a software, this thing. So all that is really important in developing IP and providing a customer support. And mind well, I had done all of that, and that's why actually I am explaining you why it is important. So it is just not an one-time effort being done and forget about it. It's a business activity, what you need to do that. Then documentation, what you need to give, flowcharts, your example of code snippets, how your RTL code, if I am giving it to your code, how your RTL code and this code can be integrated together, what kind of signals will need it, how to instantiate it, what kind of device drivers you will need it, what kind of the simulation waveforms you must see that. All that has to be a documentation there. Then only the people. It's like when you are going to ARM and you are trying to utilize it, you see there a documentation which is given. The same thing what you need to develop it over a period of time. So what is the success matrix? Functional correctness versus reference model or golden results. That you have to keep on watching it every time. There are protocol compliances and interoperability behaviors which you have to do that, because there are certain protocols which you are adhering to that. They are stress tests, long runs, whether it will continuously run for hours and years there. How do you create that? The corner case conditions. How do you create inject errors? How do you check those? All that. Whether it is giving you the performance at that rate, or you talk about saying that it will work at 100 megahertz as a design, but theoretically it is giving only 1 megahertz output. It has no meaning. So you need to check whether it is giving you at that particular way. Then whether it is got observability is there. If there are certain challenges are there, are you able to put some kind of a counters, buffer traces, triggers, so that there are debug hooks are there. If your IP's building block is given to someone and you wanted to maintain it, then you need to give actually a code there. You need to actually tap it, and that is really important one. So with this particular, I'll stop here and go to a small PCI Express development case study. But before that, actually, I would like to check with Madam how much time she can permit me. Parkal sir?
Hello, sir.
How much time you can permit me?
Basically,
Or should we stop?
maybe 5 minutes, if it is enough. So that
Okay,
we
fine.
start
So anyway, let me just run, because this is a practical example. I'd like to show and stop over here. So we develop a PCI Express IP as a case study. I will not go into what the PCI Express is there right now, because PCI Express, it has come to Gen 7 right now, right from the 1.0 specification in 2003 till 2020-25. And what we developed in 2003 I'll show you a case study which is still going on as a one, but I'll show you how the technology gets developed in India and validated to the entire world. So that's the experience I would like to share with that. So PCI Express is definitely from PCI to PCI Express is a serial bus instead of parallel bus to serial bus. It's a very high speed, and the previous slide already tells you that at what gigabits is actually gigabits per second, from 32 gigabits per second till it is 2048 gigabits per second, that is 2 mbps, 2 terabits actually per second is actually the speed which is improved at that particular level, right? And that's the way the specifications are moving ahead and you are getting high speed interconnects. So when we developed actually in 1992, it was as a first as a PCI. Then it was launched at 2002 as a PCI Express 1.0 spec. And in 2002, we demonstrated first interoperability demo with Intel in PDF, in IDF. That is Intel Developer Forum. We demonstrated a demo saying that this is how the PCI Express will work, and we showed it with the Intel's jointly, saying that this is how actually the PCI Express will work. In 2003, we were the world's first one to demonstrate in 2003 a PCI Express at 1.0 which is compliant, which is a certified PCI Express IP on NITAL's developed board from India. So that's the thing what was done over there. And what is important is actually need to do a compliance testing, saying that at that gigabit speed, are you going to meet those specifications or not, whether the physical electrical characteristics are meeting or not. That is what we need to show. Okay, and these are the different techniques which is used in the encoding decoding of as a PCI. We'll not go into that, but this is an IP what we developed in those days as a general purpose building block which was given to many people in the world, and they use this. So this is a generic IP block we developed on the board. We developed physically on the board, got it certified, we demonstrated in the world in 2003, and people used it. The companies used that, and this is a building block of that. So this was actually the documentation how the people can utilize our IP core, and this is actually 4-lane exerciser board. This was utilized in the world first demonstration over there. This was done in actually 2003. So this was into 8-lane PCI development board. This was sold by NITAL and it was utilized by everywhere else. It is a Xilinx FPGA Vertex board. Xilinx has used this board for validating their hardcore IP which is now available. But even before Xilinx, we developed an IP in PCI Express and demonstrated to the world in 2003. This is how actually it looks like as entire block if you really want to see how. So this is actually the NITA's block. It will do exercise. So we created this exerciser, and all hardware in the world, whether it is an NVIDIA card or whether it is Philips card, whether it is Intel card, Dell card, all that board used to get certified based on our tool, saying that whether it is compliant or not compliant. So in PCI SIG, the Intel used to develop in PCI SIG and utilize NITAL's board for testing it. And this is Mentor Graphics public announcement which was done in 2005, saying that Mentor Graphics, which is a part of Siemens now, has utilized NITAL PCIX builder platform and the board to certify their Vertex design with this one, and they could actually give their compliant IP. They also develop their own IP, but they utilize our what you call the
Sir, just unmute yourself. Natu sir.
I don't know which slide I was there, but I just came to a last slide, and I would like to just show these particular building, these cards. So these are the cards which actually developed. They're all FPGAs, they're all IPs, they are certified, and I would like to stop sharing over here. And if there is any particular question or something, so I don't know whether you are able to see this. This is a board which is developed there in 2003, 2005. This is a box which was used by the world's people over there in certifying it, and there are various blocks. This is a USB building block. This is Altera based board, which is actually the world first in 99 OTG, what you use today in your mobile phone. This board was used to develop your what you call your USB stick, your drivers, your voice over IP, all that was actually used on this. So sir, we can stop here, and if there are any specific just question one or two if you allow, or otherwise I'm done with that. I'll share my presentation which is as a generic part over there. I don't know whether that entire presentation will be helpful to the student. If you believe that just to have the information this will be useful to you, I am okay to do that. Right now Nital is not in functional business. We switched over a very long time, but I believe that explaining how the IPs are created, how IPs are developed using FPGA, and creating a world-class solution which is possible, that is what we demonstrated wanted to showcase in this FDP workshop. And there are a lot of things are actually available. We can take detailed design workshop also later on. Over to you, sir. Thank you so much.
Thank you very much, sir.
By the can you just take a snapshot of all this for me?
Okay, sir.
Just saying that so many people, I don't know. Thank you so much. Really excellent participation over here. I can see.
I have taken snapshots, many slides.
Yeah, that will help you. So I will sign off. If there are any questions, do let me know, sir.
Basically, there is one question in the chat box that
Okay.
I couldn't get right now.
Okay.
Maybe I will.
Okay, what is the question? Okay, let me just see.
Should I just sign out?
So the question is, does IP
Okay,
core
does IP core is actually a separate entity or it's a part of FPGA, right?
sir. Yes.
Which one? Yeah, so IP core is actually synthesizable part which goes on FPGA. If it's a hard IP, it is a part and parcel. When you buy FPGA, you will get it. If it is a soft IP core, you will be putting it over there.
Participant, if you have any questions, you can unmute and ask. Okay. I think participant number 194 have some question that put in the chat box. I have just lost. So if he's interested, he can unmute and ask the question.
Or maybe perhaps sir, you can give my phone number, email address. I am absolutely okay. They can contact me. Absolutely no problem.
Okay, sir. Okay. Thank you very much for your wonderful and enriching session, sir. On behalf of the organizing committee, I extend my sincere thanks to you for your such a informative and engaging session. And also, we truly appreciate the time and efforts you have put in devoting to share this knowledge with all the participants. Thank you, sir.
Thank you
very
so much. And my just appeal to all the participants over here, do provide your feedback and what improvements I can do. If this needs to be covered up in a small manner, that will be really good. I will share the PPT if this is useful. Absolutely no problem. Thank you so much.
Thank you, sir. Thank you so much. Now I invite our co-coordinator Doshi ma'am to invite our next speaker, Mr. Sagar Girewale. Over to you, ma'am.
Yes, sir. Once again, thanks a lot, Nathu, sir. It was impactful and really fortunate to have you as a honor of guest today.
Thank you very much, madam. I really appreciate for giving the opportunity. and I just couldn't say no to you for sure. Thank you so much.
No, sir, you're doing such a wonderful thing to the VLSI society. It was honor having you as a speaker, and let's be in touch so that we can have more contribution in
Sure,
the
sure.
VLSI semiconductor
It will be
industry, which is
my pleasure
in.
at any point of time. You people can just contact me. I'm absolutely available to anyone.
Okay, sir. Thank you. Now, the most awaited moment. Am I audible? Hello?
Yes, ma'am.
Yeah. uh, the most awaited moment and the next speaker. Without taking a break, I feel we should continue. Yes, everyone is eager and enthusiastic to hear about the next speaker. See, without the break, all of them want to hear to the next speaker. So it's an honor and privilege to introduce today's guest, who is Sagar Giravli. He's senior DFT engineer, a distinguished DFT lead with over 9 years of experience in semiconductor industry. He specialized in high performance wireless transceivers and complex SoC architectures. He's a proven expertise across advanced FinFET nodes, 6 nanometer, 14 nanometer, and 28 nanometer, with a portfolio of 10 plus successful tape outs. Currently, he's serving as a DFT engineer at Google. He brings a deep background in leading multidisciplinary teams and pioneering next generation methodologies like streaming, scan network, that is SSN, and frequent functional clock.
Ma'am, I think you are on mute.
Implementation for high performance silicon projects. He's driving architectural designs. Again, the problem. Audible?
Yes, ma'am. Yes, ma'am.
Okay. Uh, uh, he is collaborating with global design and verification teams to streamline post silicon bring up for consumer and infrastructural hardware. In Qualcomm India Private Limited, uh, he was there since 2018 to May 2025. With leadership, he directed DFT activities for wireless transceiver chips, managing a team of 4 plus engineers across three major product cycles. Then about the architecture, he owned DFT concept preparations for mixed signal IPs, scan architecture, B-scan, and M-BEAST. With advanced methodology, he successfully implemented Mentor's Tessent, that is SSN, to optimize test data volume and reduce ATE costs. Validation and debugging, he oversaw ATPG pattern generations, power optimization, and high speed simulation environments, including timing SDF. Then post silicon, he led the silicon bring up and AT pattern debug, ensuring rapid transitions from design to mass production. He was in Altran India from May 17 to November 18. He focused on M-based architecture and memory controller generation for block and SOC levels. He executed verification of memory controllers and delivered high quality AT patterns. Now, about the technical contributions and innovations, he pioneered the move to packetized scan data delivery, drastically reducing the required test pins and improving test time efficiency for RFIC chips. In high frequency testing, he developed innovative functional clock path methodologies to enable at high speed testing beyond the limits of standard OCC, capturing subtle timing defects. For clock excellence, he designed synchronous OCC architectures to eliminate coverage gaps inter-clock domain crossings. And for power optimization, he engineered AT scan pattern power management to prevent IR drop failures during high toggle tests. Now, about the awards and honors, he had 25 plus Qualstud awards for exceptional leadership, technical execution, and project ownerships. For GSOC and QBiz presenter, frequently was selected to present papers on SSN methodologies, new clocking architectures, and at speed fault coverage improvements. So the technical skills which he has are huge. He has used the tools such as Tessent for SSN, Scan, MBES, TK, then Tetramax, DFTC, then Spyglass, Conformal, LEC, Primetime, VCS, and X1. In methodologies, hierarchical ATPG, cell-aware ATPG, test point insertions, JTAG, BScan, TDF exception flows. And he is expertised in Verilog, TCL, and Pythons. Not least but last, I'm very much proud to tell you all that he's our alumni. And really, hats off to you, Sagar. And thanks a lot for honoring us by accepting our invitation to present in this FDP by ATAL. So, welcome, hearty welcome from all of us, Sagar, back again. And without wasting much more time, already you are late to utilize each second which you will be talking. Welcome once again, and over to you, Sagar.
Yeah, thanks a lot, ma'am, for this brief introduction. And yeah, first of all, I'm really proud because as alumni of SOPM and this is a fantastic opportunity that you gave to me. And yeah, sure, I'll share all the knowledge with respect to my domain. And yeah, I think without wasting time, I'll share my screen and just we can start. I hope everyone can hear me properly.
Yes, sir, all good.
Yeah, okay, great. Okay. So a topic that I'm going to present today is a feature of DFT and the silicon life cycle management. DFT, I think whenever this word comes, right, the people usually think discrete Fourier transform. Even when I started my career, I also thought, okay, it's a discrete Fourier transform, but basically it's a design for test. And many of you have basically, I think I attended yesterday's lecture and the first session today's also. So you might have gone through all these basic details and IP and basically hard IPs and SOCs and all, right? So and you might have seen that all these technology nodes and on that entire SoC, we have 90 billion plus transistors, right? So what if there is a manufacturing defect, and how will you be able to basically find out where exactly the issue or defect is, right? So this is where a DFT comes in picture. So DFT basically is a design for test, and there are multiple basically areas under DFT, and I will basically I will start with the basically you might have seen in sorry, just a minute. Mostly in ASIC design, right? So usually you will not see. Sorry, I'm not able to remove this. Sorry, just allow a minute. Yeah. I will basically start with as design flow, where I'll just mention where the DFT comes. So DFT basically comes in. There are two different we basically call front end and back end. So DFT engineers basically they work on the front end side also and back end side also. Okay, so basically you might have seen in that ASIC design flow, right? First, basically, oh, sorry. First, ATAL design, and then we have basically the verification. I'll just go over the basic ASIC design flow, and then basically synthesis, and basically you might have seen there's a place and route.
Sagar, sorry to interrupt. Can you change the
Yeah.
color? Can you make it white so that it will be visible?
Oh, actually, it's a PDF, so oh, you're not able to hear.
No. What you are writing,
Oh, okay, okay, sure.
because the background is black. White will
Yeah.
make it
Okay.
more.
Yeah. Okay. Yeah. Better now. Yes. Okay.
Yes.
So yeah. So place and route, and then basically we have STA layout, right? All these basically different. Sorry, I'm basically joined through iPad. So yeah, you'll see that little bit here and there. But yeah. So as you can see, this is the basic ASCII design flow, and DFT is basically this part basically in every basically company, right? There are different uh, the section, right? Some sections in like the front end, back end, right? So this basically is the front end, and this is the back end. Okay, so DFT is basically comes in both. So DFT engineer basically get involved in all the phases here, basically starting from article design. So article design, and then in between synthesis, and then this is where in this section, right, this is where DFT logic is getting added to the design, the actual functional design. And basically with respect to that, then that entire the DFT logic, right, basically that also will be uh, goes through this place and route and the STA and uh, all that ASIC basically domains. Uh, so uh, I'll be basically the roadmap point of view. I'll be go over the fundamentals, then fault model, and basically the what is the scan design. So these are the basic of the DFD. I'll just go over. I think many of uh, in the curriculum, right? I think we have very limited basically some chapters we can say, or with respect to DFT, and so I'll basically go over the basic, and then at the end I'll just go over the current trends, and what are the challenges in DFT, and what are the basic or which all important uh, basically ways of DFT to minimize the challenges, right? So first I'll go the fundamentals, and then basically there are certain, as I mentioned, advanced DFT techniques, right? And then at the end, silicon life cycle management. Uh, all that I will cover in the this particular presentation. And if anyone has any questions, we can straight away ask. We can go over this. Consider this as a kind of lecture, and maybe I will in between I'll go to other slide also. I'll just explain there the normal basically whiteboard, and I will explain some part in that whiteboard also. Okay, so basically, as you have in the previous lecture also, right? You might have seen that because of scaling and all, right? So entire SoC has basically the trillions, billions of transistors, right? And basically because of this high density, right? So there's a possibility of the defects, right? And it is very small design, right? It's like some chips are basically less than a finger size also, right? So it is very difficult to basically identify where exactly the issue, right? So there are different DFT techniques uh, which basically used during the IP creation, or maybe any chip, any IC creation, integrated circuit creation. So and important thing is basically with the DFT, right? We need to basically uh, at the end, right? Let's say we manufacture thousands basically chips. So we have to make sure that all the thousand chips are uh, basically they are good, and there are no particular manufacturing defect, right? So ideally 100%, basically you might have heard there's a yield. Okay, 100% is yield is not possible. So usually in every company, right, based on the uh, the purpose of chips, right? Basically it's a mobile chips or it's automobile chips or this medical and all, right? So based on the uh, purpose of that particular chip, right? So that yield percentage or the how much test coverage basically that we are test coverage in the sense like how many basically fault site that we are covering, right? So all that basically changes based on the purpose of the chips or where the application instead of purpose I can say application, right? So where we use that particular chip, right? So main thing is like basically we need to achieve that quality. We have to basically find out the defects here, and there are certain steps also. Basically, once the chip is manufactured, right? So it goes to the silicon bring up. Silicon bring up is basically that entire. Basically, we have the wafer, right? So we have multiple dies on that wafer. Okay, so we have the die level testing, and then after that we have package level testing, and then basically the field side testing. So basically it's called as a RMA or maybe actual customer sample based testing also. So each level testing, right, it has very significant cost. Uh, Basically, every stage, right, it has basically it is based on the cost here. So adding basically, let's say you have this small chips, right, without DFT, right. So it is very difficult to identify, and you'll not be able to basically identify which is a good die or bad die, right? So, and let's say if you're using that particular chip in automobile, and what happens, it will basically goes for a toss, right? So, I mean, there'll be a major accident and all, right? So we have to make sure that every chip goes through that proper testing and all, and we need to achieve that certain the percentage of the yield uh, to get the better quality of the chips here. Okay. So, as I mentioned, right, there are different kind of defects here, right? So, let's say there's a while manufacturing, right, there may be some a stuck issue, maybe certain fault site or certain node is connected to the VDD, certain node is connected to ground. Then there is a during handling also, like let's say there is a crack on the chip, right? So these are the basically different kind of manufacturing defects, right? So that basically we need to identify with respect to this DFT. Okay, so uh, based on during this IP creation or maybe the chip creation, right? So a DFT, we put DFT logic into design. So along with the functional logics, which I'll be covering in the next, how we are basically inserting that logic, and then how we generate particular the patterns or we call it the vectors, right? And we have to basically verify those pattern also. There are different kind of tools. I think Madam just mentioned in my intro for the pattern generation. There are different EDA companies, right? You might have heard Mental Graphics, Cadence, and Synopsys, right? So we have tons of different tools. So every company uses the tools, generate the patterns, they verify it, and then based on that, when the chip is manufactured, same patterns basically get ported to that silicon, and basically we identify where is the defect and which is a good die and bad die. Okay, and as I mentioned, this field return and strategy DFT, right? So which I'll be covering the next slides. So far, anyone has any questions like? Okay, I'll go to the next one. So I'll start with the DFT fundamentals and the main important pillars, right? The controllability and observability, because chip is like really small, right? Let's say, for example, I'll just give an example here. Let's say this is one AND gate, right? Just simple one, and this is one OR gate here. Okay, so basically control means what? For example, we have to give, let's say, one value here, right? We have to control this particular nodes here. So these are the fault side we call the AND gate fault side is basically two input and one output, right? This is called the fault side or nodes, right? So this I'll be saying fault side or nodes, so you can maybe assume, I mean, you can understand that way. So we have to, let's say we have to give one value here. That means I'm controlling that node of this particular, the second OR gate here, right? And let's say this output, right? Now let's say the one input to the OR gate, so output will come one only. Now I need to observe that value at the output. So now this is just small example, but let's say we have, as I mentioned, that billions or trillions of transistors, right? So that design is really big, and that every node basically we need to target, and we need to control that node, and basically we need to get uh, value basically, or observe value at the output side, right? Because we have limited number of pins from the top level. We have access on AT, right? We have access to only this legs. We don't have access to this leg. So how basically we are going to control that each nodes, and how we are going to observe it, right? This is where these are the main thing: controllability and observability, right? These are the pillars of the DFT here. Okay, so as I mentioned, right, DFT is basically designed for stability, right? So objective is basically, as I mentioned earlier, right, we have to basically find the defect, okay, in the manufacturing, whatever the chip that we have manufactured, right? So we have to identify the which chip is good and bad. So that means we have to find the defect. So, and there are multiple kind of defects which I already mentioned. There's a stuck and uh, uh, due to handling issues and all, right? So there are different kind of defects. So that we need to identify with the DFT, and we have to basically find out which is a good and bad silicon or bad die. Okay, and how we're going to do it? We have to basically control each node of the design, and we have to observe that each node of that particular design. So controllability and observability both comes in picture. Okay, we have to achieve it together here. So you people might have said, what is it? What is now we have different domain, right? As I mentioned, we have RTL design and verification, right? So in verification also, right, we are doing that verification, right? So how it is different than verification, right? DFT is how it is different, right? So I'll just give an example, like as I mentioned here, fault site, right? And in between I have mentioned patterns also, or vectors also. So to test the AND gate, right? Let's say this is my chip, AND gate is my chip here. To test the AND gate, how many basically inputs we need? Basically, there are two inputs right here. So how many patterns we have? So AND gate is basically we have. So again, how many patterns is basically 2 raised to n here. So basically we have two inputs here. So 2 raised to, so 4, right? So we have 0, 0, 0, 1, 1, 0, 1, 1, right? So we can call this as a pattern here. Okay. So we have to basically use these patterns on the AT, and we need to make sure that the simple example here, let's say I mentioned there is stuck issue, right? So let's say this particular node is connected to, let's say, ground here, right? So when if you give 1, 1 here, you'll always get a 0 output here, right? That means your chip is not properly working, correct? So this particular, so 0, 0 or 1, 1 pattern, right? It will find out, okay, oh, my chip is not properly working. So we need to find out where exactly the issue, right? So, and what kind of basically fault is there, and which we need to find out. Okay. Or let's say OR gate is there, and basically this particular node is, right, this is basically uh, uh, stuck to the VDD, right? Or VDD. So this will be always 1, right? So even if you give, let's say, 0, 0, output will be always 1 here. Okay. So this one I have mentioned, right? This we call it a stuck at 0. Okay. And this one is we call it stuck at 1 here. Okay. Which I'll be covering in the next slides. But this is basically, now you might have got the little idea, right? What is DFT, right? And now what are the patterns or vectors that we are basically giving once the chip is manufactured, and how we basically get to know which one is a good silicon or good die or bad die, right? Are you on the track here? Maybe you can give some thumbs up in between so that I can say people are listening and they're correlating with the ongoing session. Okay. Okay. Now, as I mentioned, right, so there are different kind of uh, different stages, right? When chip is manufactured, right? So there are different kind of testings, right? So we have fab level, the package level, the board level, right? And a field use here. So you can see, right? This is just overall, right? Kind of average out basically with this different kind of technology and all. So you can see this fab level basically just, we can just assume it like uh, per second basically kind of cost here, let's say $0.1, right? For fab level, package level, let's say $1, right? And system level $10, and field level basically 1,000. Field level means, let's say these are the basically you calculate as a customer sample. So customer samples, they are already integrated that particular chip right into their basically uh, 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 at their end or their particular application they have already used, but okay, they are seeing some issues and all, right? So we need to help them and to identify where exactly the issue, whether it's which particular defect is there, whether it's during handling there is some crack on that particular die or not, right? So these called basically the failures. So you can see at that level we have the cost is very high here. So we need to basically first of all find let's say as I mentioned, we have 1,000 basically chip manufacturer, right? We have to basically understand and we need to basically find out how many good chips are there, right? So that means let's say we have 900 chips, let's say 900 chips are good, so I have achieved 90% failure. So those 90% 900 chips, right, that I'll be basically, it will go through the package and then board level and actual basically they will sell it to the customer here. Now let's say without DFT, you will basically give all this remaining the faulty die also, right, to the customer if you sell it and if they use it at their end, right? So there might be some malfunctioning and all, right? There may be different or very critical situation, right? In the, if let's say in automobile, right, if you use it, there'll be the accident chances. Let's say your servo, your sensor is not working, or maybe your ADAS is not working, right? So this kind of different kind of feature that we are using nowadays in different uh, let's say car or maybe in the medical, right? So there are a different kind of challenges, right? Or so that's why we need to basically achieve that yield, and then let's say we have very limited number of let's say now, let's say I 900 we found out they're a good die and they basically we have sold to the customer, right? So we know here like already in these levels we have already tested these 900 chips, so we know there are very let's say there are no issues in this one. Now there could be some handling issues and some crack issues there, right? So those kind of issues are very easy to find out at this level, so we can basically cut down the cost at this stage here. Okay, so that way basically we have to analyze and basically to reduce the cost here, because addition of DFT, right, it is basically extra area, right, of the design. There is no use, right? Let's say you are basically able to find out or let's say 100% without DFT, right? So you know there is no manufacturing defect and all, there is no use of DFT. But that is in reality, right? It is not possible, right? Maybe there is human error or maybe some unforeseen errors, right? So that you cannot basically predict and you cannot basically understand, or you cannot find out those defects here. So this is where DFT is very, very important for every chips, whichever chip is basically getting manufactured, right? It has to go through DFT, all the testing, and we need to make sure that the good silicon and bad silicon here. Okay. Yeah, I hope you got some little idea so far. So as I mentioned, two pillars, the controllability, right? So what is the controllability? We have to basically uh, control that particular node here. Okay. So for example, this is just one. I'll cover this particular diagram which I shown here, right, in the next slide. But controllability means basically, as you can see, this is a functional path and this is the combinational logic here. So maybe I can just draw one again AND gate, and then AND gate output is basically going to here T. So this D2 key is a functional path here, and this ESI to Q, right? This is basically the DFT path, or we call it the scan path here. Okay, so which I'll be covering in the next one. So now what happens, right? So earlier I mentioned there's a 2 raised to n rule here, right? So AND gate, basically there are only two inputs here. Now let's consider there are thousands of we have one chip, we have thousands basically functional ports here. So 2 raised to 1,000, these many patterns, right? So to test those patterns, it will take ages to basically test those patterns, right? Because these many patterns will get created and we need to test, right? It will take, let's say, in years, right? 50 years and 100 years, right? It is not even feasible at all, right? So that's why we have different DFT or scan architectures, basically that we insert in the design. And with the limited number of pins, right? We basically test entire chips here. We control this particular end. So from this particular kind of this, as I mentioned here, the SI to Q, SI to Q again at this level, SI to Q at this level. This is my basically scan path here. Okay. So with the limited number of SI ports here. Let's say out of thousands, right? So we have, let's say we got only 10 basically inputs, okay, for a DFT, 10 inputs and 10 outputs here. Okay, we have only 10. So basically you can see 2 raised to 10. Anyway, we have limited number of patterns will get generated, but again there are different ways also to reduce that pattern counts. Okay, we don't know, let's say in AND gate, right? Let's say 0 0 1 0 0 1 and 1 1, right? So to identify the stuck at 0, stuck at 1 faults, right? So we don't need all the patterns. Okay, so we need only 3 different patterns here. So we have different ways to reduce that pattern count also. Even though let's say 2 raised to 10, let's say these many patterns will be generated, so we have certain ways to reduce that pattern also. So why we have to reduce it? Because again on AT, right, I have, as I mentioned in the this one, right? So every level it is basically per second charges, or different companies have different ways or the charges, right? So these are the charges, right? So if you have limited number of patterns, your test cost will be very less, right? So this is the advantage here. And let's say there are like every company, that let's say Intel, Qualcomm, and Google, right? Google recently I mean, there before, but they started recently their in-house basically all the chip design and all. To basically, they are basically every year they're manufacturing basically billions of chips, right? Because every electronics need this kind of these chips. Say, uh, uh, if you basically, just for example, right? So I work on RF transceiver, which was a basically you might have seen that we have 3G 4G chips, right, in every mobile, right? So so this is called basically called a modem here. So in every modem basically we have certain receivers and transceivers here. Okay, so the modem is basically all this IP, right? Let's consider this is modem here. So all these different projects are there. Let's say I'll be working on these projects. Okay, so other team is working on this particular projects, and then another team is working on this particular projects here. So at the end, on the SoC, we are basically put all these things on package, you can say, right? Or board, we can say. We'll put all these chips, and then we'll test it again. Okay, whether my this operation of this entire SoC is proper or not, right? So there are like billions of basically chips are getting manufactured. We need to basically test all the chips. So you can see, right, billions of chips. Let's say even it's a $1, right? So you can see the cost here. I mean, it is not. I just give example, but yeah, there are different ways to basically test it. So you can see in one the project that I have worked on, right? So the entire all those DFT related vectors. So we have basically ATPG vectors. We have embed vectors. I'll be covering all these things, but I'm just telling you now here which are different type of patterns. Then ATPG embed vectors. Then we have IDDQ vectors. Then in this IDDQ comes under ATPG only, but yeah, in that we have stuck at vectors. Then at speed vectors. So all these vectors basically testing time was less than basically around 1 second. Okay, so you can see and you can say the overall functional ports, right, for that particular chips. I'll use the ballpark number. So there was around 2000 basically functional IOs here. Okay, so you can see 2 raised to 2000. So you can see if we do not use DFT, right? So these main patterns will get created, and you can see the test time, right? It will take, as I mentioned, right, more than 50 years, 100 years. I mean, it is not even feasible at all, right? But with the help of DFT, right, we have tested entire basically that particular chip in just basically 1 second. Okay, around 1 second. Yeah. And we had out of 2000, right, we had limited, let's say, 15 IOs only, and 15 inputs and 15 outputs here. And some for taps, we have, let's say, dedicated ports like TDI, TMS, TRSD, right? So ballpark number is 15, 15, 30, around 35 basically IOs were available for the DFT. So with the help of these IOs, we have basically cover entire that particular chip, and we have tested under 1 second. So now you might have got the idea, right? So why DFT is important for every chip here. Okay, any questions so far? Okay, now so as I mentioned, right, controllability. Now what happens, right? Let's say I want basically here, I want to basically test stuck at 0. Stuck at 0 means like say, this AND gate I'll be drawing here. Okay, stuck at 0, right? So what input do I need to give to check whether it's stuck at 0? So this input anyway, this I need to give 1 only. So here also I need to give 1. Then only I'll be finding out whether it's stuck at 0 or stuck at 1, right? Let's say in this is basically stuck at 1. If I get 1 1, then only I'll be let's say this particular one is stuck at 0. I'll be always getting 0. That means there is a issue. So these patterns basically will basically uh, help to identify whether this is a stuck at 0 fault or not, right? So how I will control that particular node? So this particular scan path, right? I'll just zoom in a little bit. So this particular scan path. So let's say I'll be calling this all these 3 flops, and this from SI to Q again. This particular path, SI to Q, again SI to Q. This is a scan chain here. Okay, so I have basically 3 different flops here. Okay, so in and every output of Q, right, it is going to certain combination logics here. Again, it is getting observing here. So in just three cycles, I can control this particular node here, right? So let's say I have 3 flops, so I'll be giving, let's say, 1 0 1 here. So after completion of 3 cycle, that we call as shift in. Okay, so 1 will be here because at the end of the 3rd cycle, right? Basically, this 1 will be here. Okay, I cannot draw it here on this one, but you can say 1 here, 0 here on this Q, and 1 here on this Q. So this Q will directly go to this particular AND gate, and we can control that particular node here, right? Now, how we can observe it? Now, let's say AND gate. Let's say AND gate. This particular leg is always basically with the functionality, right? Let's say in my design, this is always tied to 1. Okay, I know. Okay, this is tied to 1 here. Now I need to only cover this particular node here. So already this is 1 and this is 1. So output will be 1 here. So now this is where I need to now observe this particular node here. So this node basically will come to this particular flop here. Okay. After the shift here. So in the capture window, this output 1 will come to this D here. Okay. So I'll be covering what is shift, what is capture, and what is shift out here. So this particular flop in the next slide, but I'll just quickly explain it here. So this one will get basically captured by this flop. Okay, basically launch and capture, and basically once we get the output after the captures window, then we have the shift out way. We can shift out again. Let's say now I need to basically control this particular leg, this OR gate here, right? So I'll be basically giving another pattern here. Okay, 0 1 0. Okay, or whatever is that. Okay, so in the next shift in, right? So I'll be giving 1 here. 1 will come at this particular output of the queue. Okay, in the 3 cycle completion. Okay, but by that time, when I'm doing the next shift in, I'll be basically whatever the value that I observed in the first capture, right? I'll be shifting out and I can get it at the output end here. So as I mentioned, right? So this is my entire design, and I have only one scanning ports here. Okay, this is my ESI 0, and output of this is basically I'll be drawing here. This is my ESO 0, okay, or ESO 1, or this is ESO SI 1 here. So I'll be getting value at this particular output here, right? So that means the entire design, what I did, I have shifted some value, I have controlled that particular node, then whatever the output that I got it with respect to the functional, let's consider with respect to this one. So let in other this one, this leg is another basically control through another chains. Okay, that's why I basically just for the simplicity purpose, right? I just tied to 1, but in real scenario, this again node basically control through another scan chains here. Okay, so that also when I'm giving here, so as I mentioned, there are different EDA companies, right? So all these EDA companies basically that they are offering those tools, right? ADPG tools and all. So those tools are intelligent enough when I'm basically targeting this particular faults. That time basically another pattern, right? That same pattern basically will go and it will give the 1 value here. Okay, so that means I'll be covering basically stuck at 0 for this particular AND gate, and then I'll be observing this one. So for this one, let's say what I'm doing, I'm basically shifting the value. Then what are the values that going to combinational logics? that value is basically getting observed, and again that whatever the observed value is basically shipped out, right? So yeah, this is the overall one, continuity and observability. Okay, so we have controlled this particular node, and we have observed this particular node here. Okay, so this is the same thing. So uh, coming to the fault models here. So there are like different fault model as I mentioned earlier. So stuck at models, like stuck at 0, stuck at 1, there's a transition delay. I think if yesterday's lecture, right, you might have seen that delays here, right? There's a slow to rise and slow to fall. That means 0 to 1 and 1 to 0, right? So in the real scenario, this is like basically, let's say this is ideal waveform here, right? But in real scenario, right, this it will not go suddenly one, right? It will take some time, and then it will like this, right? So it takes some time here. Okay, so this is basically slow to rise and slow to fall. So this basically comes under the dynamic fault models that we call as a transition delay faults, or we can call as a at speed faults also. And there are some physical faults also, the bridging and all. Then there are some IDDQ, the leakage current. I think yesterday I forgot the uh, uh, name of the basically, uh, I think Vinay Sharma, right? Yeah. So
Yes,
he has
yes, Vinay
mentioned some.
Sharma from NI2
Yes,
Logic.
yes, yes, yes. So the sir has mentioned like really good, like there are leakage issues also, right? So those also basically we need to calculate the leakage also. Okay. So why there is leakage, where exactly the for that particular fault is there. So those leakage related faults we cover with the IDTQ faults. Okay. So that also I'll be covering the next slides. But these are the different type of faults. I just put the basic. There are some MBase related also. There are also some coupling faults and all. But I'll be covering only basics. Based on time, I'll see whether if I get time on the MBase, I will cover on MBase side. Okay. So uh, so just for simplicity, we have stuck at, then we have transition delay faults, then we have bridging faults, then we have IDTQ faults here. Okay. So uh, Stacked 0, as I mentioned earlier, is very simple, like short to ground or short to VDD here. Okay. So industry requirement is basically is 99 more than 99% coverage here, right? So what is the coverage here? So as I mentioned here, let's say this is my AND gate here, okay, and my fault sites are basically here 3, right? So if I'm covering all three sites, I'll be getting 100% coverage here, right? Now let's say uh, look, we have to basically find out each and every node, okay, because functional test cases, right, uh, as I mentioned, because of the huge IO count, right, and they functionally basically they have basically, let's say this is our entire chips and this is particular feature that they have inserted, this is again certain features they have inserted. Okay, this is actual functional logic here. Okay, so they have basic test case basically with respect to feature wise. Okay, so they are not covering the entire basically logics uh, of the chip at a time, right? So with the stacked fault, right, basically for this DFT methodology, we can basically check each and every node of the design. Let's say now they're basically covering the functional test. They have certain patterns, but the feature wise. Okay, so uh, they basically on ET also they also run few test cases. Okay, now their test cases is failing. Now how will they will find out where is the issue? Then with the help of DFT, then uh, with our stacked patterns or vectors, right? So we'll run those patterns on AT uh, uh, or silicon. We'll run those patterns and we'll find out where is the issue. So there are different techniques also to identify that issue and basically to resolve that. There's a LVP, LVI, laser voltage probing, and laser voltage imaging. So some chips we recover also. Okay, and let's say let's say now this particular was you might have seen. Uh, let's say this now chip has, let's say, 10 different features, functional features. Let's say this particular feature is not working, or maybe there is some certain issue, right? So through software we disable it, and other features basically companies sell these chips to the uh, uh, customers, right? Because this particular feature is itself is not working. You might have seen recently, right? So some mobiles, right, we had only 4G range, right? But already the mobile had the 5G chips. Okay, but the uh, 5G infrastructure was not available, right? And even though chip was there, but we were getting 4G. Then once that 5G infrastructure was available, then basically all these mobile companies, right? They basically gave one update. So in that update through software, they have enabled that particular feature, right? So this is how we started getting that 5G range here. So there are certain this is again based on the features. Okay, we can disable chips and we can that particular cell, or we can identify, let's say now we understood, okay, let's say this particular node is basically stuck at to one here, right? So different techniques, as I mentioned, LVI, LVP, right? There are different other also, but these are the important one to identify where is the issue. So on the laser voltage probing and imaging, right? On the there are different kind of microscope. So we put chip under that microscope and we basically remove that stuck particular node here, right? Whether it's stuck to ground or stuck to one or VDD, right? So there are different techniques, but yeah, this is how basically our pattern when we before manufacturing, right? So we have different. So in the synthesis level, right? As I mentioned, we have in the our ASIC design flow, right? We have synthesis, right? So after synthesis, right? Before they give one netlist to the PD. PD is basically physical design. They do place and routing. Okay. Okay. So parallelly, we also or DFT also gets that particular netlist. We put our logic at netlist level. There are different ways also. Nowadays, there is a left shift. Basically, most of the logic, right? DFT logic, we put at the RT level only. Okay. And at the DFT level or at the netlist level, we just do the stitching. Okay. Stitching in the sense, all these scan chains run. As I mentioned, that scan path that I have mentioned in the earlier slide, right? So that particular stitching we just do at this end. Uh, okay. So by that time, PD will not or physical design will not wait. They will basically without DFT, and they will do some analysis. There are some different, again at PD level also, right? There are different kind of steps, um, uh, uh, pre, post, and PDP, ROR, and different kind of basically steps are there. So initially they will start work with this actual functional netlist, and once this DFT based netlist is available, then we basically release that netlist to again PD. Okay, so they will again basically switch that functional netlist to the DFT netlist, and they will do some pleasant route. There are different, basically we have to based on the floor plan and all. Floor plan is basically uh, so this is my chip, right? So there are different kind of cores. Let's say I have 4 different cores. Okay, so uh, so when we do the DFT, right? So this ad hoc DFT, basically legacy, right? There is completely flat. So from the top level only, we used to basically put entire logic with the help of different EDA tools. Okay, but now what happens, right? Let's say if there is issue with respect to this one, okay, this particular core. So again, we need to basically reinsert that our logic, right? To avoid that, right? We have every company is now they are using the hierarchical approach. What is a hierarchical approach? So will be basically inserting that particular logic for each core. Core in the sense, like you can say a certain section of that particular chip. Okay, so I in this one, let's say this is my chip, this is my core 1, core 3, core 4 here. Okay, so all these cores basically TFT insertion or that after this level, right? This creating the scan chains and all, and there are different few more basically steps are there. So all that basically we do core wise here. Okay, then once we do it separately, right? Then at the top level we just integrate it. So this is how we use the hierarchical approach here. Okay, so as you can see, right now this is where the DFT comes in picture. Now again, PD will basically do the place and route with the DFT, and then there will be an ST. So again, we need to basically make sure that as you can see here, right? So I'll just go back. Now again, this scan path also, right? So functional team, right? So functional team basically they will basically cover the timing closure. Timing closure in the sense setup and hold basically closure, right? Setup and hold timing closure. So they will basically take care of functional path, basically D to Q. But DFT perspective, we have to basically make sure that the SI to Q path, right, it is properly met, right? Setup and hold properly met. So again, as I mentioned in the beginning, right? So we have to basically work in the front end and the back end side also. Okay. So again, this STA, static timing analysis. You might have heard this particular word. So it's a static time analysis. So we have to close the timing here. So all the nodes, wherever the entire design, we have to close the timing. Otherwise, in the real scenario, right? So without any timing closure, it is very difficult, right? Basically, let's say from this flock, right? So let's say we have two different flocks. Let's say this is q to t here, right? So now this clock, we already let's say some values here. It's a 0 to 1 value. So once we get this clock, okay, at this age, we launch that particular value, okay. But this clock, right? This clock, there's a lot of buffering here, and data is already reached, but your clock is not coming at that particular time, right? So what we are going to do, you'll just delay this particular path here, right? So that you will meet that setup and hold requirement here, right? So this kind of, basically we have to add certain buffering, certain inverters and all in the clock path, in the data path, right? And we need to make sure that each particular nodes, right, that we are covering, the timing is properly closed, right? So that way only on the real chip uh, uh, the functionality will work here. Okay. Yeah. Now this is the interesting one, the transition delay faults, or we call it at speed one. So yeah, if you yesterday you have seen, right? There's a MOSFET, right? There's a P and N type, right? So each has different basically delays here, right? So as I mentioned here, this is our like ideal basically 0 to 1 transition and 1 to 0 transition here, right? But in real scenario, it will be like this, right? So this is called slow to rise and slow to fall. So why it is important here? Now let's understand here. Again, I'll be taking I'll be taking hand gate only every time, okay? Because it is easy to explain, okay? So now this leg here. Now earlier in stuck at one, right? What we just check by the way that this particular node is stuck to 0, stuck to VDD, right? Or this node also. Okay, so all these three nodes we need to basically make sure, right? But here now let's consider this, all these three nodes are proper. They are not stuck to 0, stuck to 1, but still it is failing. So this kind of faults then comes in picture at speed or transition delay. Okay, so what happens, right? Let's say this input to this particular this one, right? This is already 1, right? It is not exactly the 0 to 1 like sharp right angle, but yeah, it is already 1 coming. But this particular leg, right, is taking a lot of time to become 1 here. Okay, so this is where basically slow to rise faults will comes in picture here. So that way we are expecting 1. Okay, let's say the previous stage was 0 to 1. Okay, we were expecting like output will go to 1, but it is not going, right? By that time again it becomes 0 here, right? So this is how that slow to rise, and again the same scenario for the uh, uh, slow to fall also, basically 1 to 0 transition also. Okay, so these are the two different basically faults that we covered in this particular faults. Okay, and this basically we cover in the functional frequency. Okay, and stuck at we cover at the shift frequency. I'll be covering that also the coming slides. Okay, so you can see stuck basically used to basically just check the whether there is no uh, any kind of mapping defect which is to stuck at 0 or stuck at 1, and in the and that we are basically all these patterns and all, right, that we have generated, and all this basically clock the frequency and all this particular clock here, right? Okay, this you can see this red highlighted in red, right? The clock signal. This will be working on the shift frequency. So shift frequency basically every company are different. Some 50 megahertz, okay, some 100 megahertz, okay, and let's say 150 megahertz, okay. So there will different shift frequencies here, okay, because again this path timing closure also there are certain challenges. If I get time, I'll cover that also. But we have only this kind of, let's say 50, 100 megahertz, 150 megahertz frequency only we are using for the this particular shift path. Okay, and then in capture also we are using same clock for the capturing purpose also. Okay, but in at speed, in at speed 1, this is why we call it a transition or at speed faults here. So we are using the functional clock frequency, because DFT, as I mentioned earlier, right? So why we are using DFT? Because functional test cases or functional patterns, they are not able to find the defects. Okay, so that's why we have to basically use the DFT to identify those defects. Now, again, let's say the question again will be like, let's say if I'm using slow frequency, let's say 100 megahertz, 150 megahertz, right? How we will be able to identify the particular defects? Okay, so that's why we have different techniques called transition delay faults. With that, we'll be using same as functional frequency in the capture window. I'll cover that also. But we are using, let's say there's a 1 gigahertz or let's say 500 megahertz actual frequency. Okay, sorry, my writing is not proper here. 500 megahertz or let's say 250 megahertz. Okay, so again there will be like different domains also. I think in previous session, right? There's a clock domain crossing here, right? So there are like asynchronous and synchronous domain also. Okay, so in asynchronous domain, usually we have always a false path. We are not covering. Let's say, for example, DFT perspective, I'm telling in the functionally, they are using the synchronizer, right? The FIFO and all that you have in the previous lecture you have seen that, but this particular async one, right? Let's say this is clock one and this is clock two, and these are the async one. Okay, so functionally, basically, we are not covering that. So whatever the let's say we have from Q to D here, right? Here. So this path is DFT doesn't cover it. Okay, even functionally also most of the companies, right? They don't cover that. There are certain features also, right? This is where we need, like in the previous lecture you have seen, right? There are certain FIPOs and all that we use, and certain logics only we can cover in that way. Okay, but let's not go into that part. But you can say we have basically synchronous and asynchronous. Okay, so again, because covering again that, right, we have to add that synchronous and all that. There are different technicals. So in DFT also, basically, we have kind of synchronous OCC, which will basically take care of this pulsing of the C1 and C2, clock 1 and clock 2, okay, to cover that synchronous domain only, not asynchronous only. Now C1 and C2 synchronous. What is synchronous basically? So let's say this is your 1000 megas clock, okay, this is going to that particular logic here, okay, and again this is a divider, this is a div by 2, okay, and it is giving basically here 500, okay, and this is going to different domain here, okay. This is 1000 and this is 500. Now this is basically your synchronous clocks here, right? So this basically going, and what are the logic in between this, right? Synchronous domain. Okay, so that we have to basically cover it. Okay, so this is where we have different technique, like we call it the synchronous OCC. So we basically put that synchronous OCC and on this path here. Okay, so that OCC will have both the inputs 1000 and 500, and basically we have to align that. Basically, this OCC will align that edges, basically slow to right, this one, and while launching, right, let's say we have this kind of this one. Okay, so when we are basically from fast to slow and slow to fast, right, we have to align that edges here to make sure that when we launch from, let's say this is 1000, this is 500, when we launch that time, before basically launching the next one, this flop should basically capture that whatever the launch value. Let's say we have launched 0 here in that cycle. In this cycle, we have launched 0 here. The 0 will come. So this flop should capture that 0, okay, before that next cycle comes to this particular C1 here. Okay, so this is how we have to align that basically clock, basically CDC, clock domain crossing here, and we need to basically cover that follows. Again, this is again one node right here. This is again D2Q right here. Okay, this is again one functional node. We have just basically inserted or this particular flops here. Again, one more thing. Let's say ideally right here. So in every functional path, we have one extra delay here, right? Because we're adding one flop here, right? And so in some cases there are flops, some cases it is not. But yeah, there's a penalty here, like one extra cycle is in the functional path also. Okay, so we'll be basically covering this particular node also. Okay, why we need it? Let's say if we do not cover, okay, let's say there is no functional test case to cover this particular logic or this particular node here. So this is where DFT team basically cover this with respect to their DFT methodology. Let's say, for example, this is synchronous OCC. With that, we are basically covering that domain crossing here. Okay, with the synchronous domain crossing, we can say, okay, and we can basically cover that. So let's say if there any defect on this leg, okay, we can uh, cover this logics and we can identify that particular defect here. Okay, so this is called basically transition delay or at speed testing. Okay, so and again, yesterday I think sir mentioned this. I think you can one thing I have observed every session, right? If you basically properly listen to that each and every word, right, you'll align to the next session. Yeah, right. So you have seen here, right, the delays and all, right, all that delay. It is not right. It is not. It yesterday also, right, in that simulation you have seen it was like this, right? So there was certain delay between 0 to 1 and 1 to 0, right? Now we are using that kind of concept and we are just putting here and we are basically now I have mentioned it's called a transition delay faults. Okay, so now why that what is that fault? This fault is basically one leg will come early and the other leg will take a lot of time, so that is slow to rise faults, right? So this is how we have to cover that also, right? So every session has basically some knowledge basically that can be covered in the next one, or maybe some follow basically concept which will be covered in the next session, right? So yeah, please listen properly so that you will correlate that each and every concept to the next session. Okay, now yesterday I think also you might have heard this wire delay, right? So wire delay, what is wire delay? Let's say from this to this, right, is a very sorry. Okay, the critical path is here, the path is very long here. Okay, so in between, let's say this is one wire here or node here, right? Node is basically, you can say, just simple wire here, right? So from which connects to one two different basically pin or port of the uh, particular logic here, right? So this particular path is very critical. So this is where, let's say you already, let's say there is no now first we have seen there is a uh, stuck at one. Let's say there is no stuck at zero fault, stuck at one fault. Now next one is a transition delay. Let's say there is no transition delay faults. Now the next part is a path delay, right? So from one node to another node, data should not get lost because of the wire delay, right? So there's a different kind of faults. There's a path delay faults. Again, we have different kind of techniques to cover that particular path here. Okay, and you can see this is because of small delay. It's very critical paths and very crucial basically. If you have basically uh, very big design, right, billions of transistors here, there will be certain critical paths which we can basically achieve with respect to this. Otherwise, let's say if we cannot cover with respect to DFT, right, and functionally also there is no particular test case, so it's a loss, right? You'll not be find out whether it's a good die or by bad die. Okay, right? So each fault is very important and each fault is depending on the next one, right? Let's say already you're stuck at one itself is failing. Okay, there is no point to test the next one, right? This is first we need to fix this one. We need to identify what is the issue, right? Because let's say this leg is already AND gate, right? AND gate is already stuck at this is stuck at one, right? So we don't have to worry about that whether it's a slow to rise or slow to fall for this particular node here, right? Because stuck at fault itself is failing here, right? Already there's a defect on this particular node, right? So we have to basically find out what kind of fault is there, and as I mentioned, like we have different kind of faults here to cover that particular node here. So these kind of rigorous fault methods we have, and we basically kind of find that particular defects, what kind of defects we have after manufacturing it with the help of this fault models. Okay, so now you can see this wire delay, a little the small delay defects, right? So this we can cover with the fault delay faults. Okay, or modeling you can see. Okay, now any questions so far? Let me know if I'm going really fast, or maybe I can slow it down. I can maybe cover
Hello.
that. Yes.
Sagar, I have one question, that is how
Yes.
skew clock issues are detected and what are the probable solution for that?
Okay, that's what the skew clocks and all, right? As I mentioned earlier, we have that this STA, right? Okay, so we have to basically make sure that all this basically, if there is a skew or anything on that particular clock path, right? Or there is a delay, right? Or there's a
But
latency on that clock path, right?
how you are going to detect it, but first of all, okay, because there are so
So
many
okay,
calls.
okay, so that's what. So there we have entire design, right? So as I mentioned, we have different kind of EDA tools. Let's say most widely used is a prime time tool. Okay, that is Synopsys prime time tool. Okay, so that tool basically we use for the uh, timing analysis. Okay, so that tool will give where exactly that basically violation is there. Okay, timing violation is there. Okay, so we need to analyze that particular path. Okay, let's say we got the violation on this particular path here, D2Q here. Okay, sorry, just give a minute. Sorry, just a minute. I'm sorry for interruption. Okay, so we have different kind of tools, as I mentioned, prime time tools, right? So that particular tool will give you all the set of faults, hold violations, and there's the clock skew related issues and all, right? So all these things basically we have to basically analyze each and every failing path here. Okay, and we need to make sure that there's a skew issues there, or it's a setup issues there, or hold issues there, right? Everything basically we take care in this stage here. ST. Okay, as I mentioned here, right, there is a for example, right, let's say this particular clock, right? Now let's say this is the clock 1 right here now, and this is the clock 2 here. Okay, so you have launched the data from this one, and suddenly right away this next clock is coming, right? So you lose the data, right? Because this second clock will not be able to capture that particular data. Correct. So what you need to do, you need to delay this clock little bit, right? To make sure that there's a proper launch and capture. Okay, launch from this one and capture from this particular second clock here. Okay, so what you need to do, you need to, as I mentioned earlier, we have to delay this clock little bit, so that you can see this clock will come at this point. Okay, so before the next edge, this edge will basically capture the data here. You got my point? Because see, right away at this point, it from this particular node, it needs some time to reach here, right? In real scenario, correct? So right away, if the clock is coming at suddenly, right? So you will lose that particular data, right? So this is why, that's why we have to basically put some buffering and all, right? So at this stage, we have to analyze all these paths where it's a clock skew issue or latency issues or setup and hold, all these issues. Okay, I'll be covering the aging simulation also later on. So that also basically I'll cover, and the duty cycle distortion. You might have DCD, right? Duty cycle
There is one
distortion,
more
right?
question. There is one
Yes.
more question from Dipali Kare, madam. That is, which
Mhm.
fault model is largely suitable for SAF or TDF?
Sorry, I didn't get the question. Which fault model?
Is largely suitable for stuck at fault and TDF.
Okay. So as I mentioned earlier, right, each fault model is a different this one, right? So as I mentioned in the sometime back, so each fault is depending on each one. Like let's say if you're stuck at 0 is very important here initially, because as I mentioned earlier, if it's already that particular node itself is basically stuck to high or stuck to ground, right? So there is no use of test the transition delay faults, right? So each fault is very important, and each fault is depending on each other, right? So there is no specific way like which is very important and all. I mean, which one has a highest priority? Each fault is important to basically identify what kind of defect is there. At the end goal is basically finding the defect in the manufacturing chip, right? Whether that's why these different kind of faults, and each faults we have different kind of patterns. We have patterns or basically vectors that I have already explained, right? What is the patterns or vectors? So each faults will have, let's say, different kind of patterns that we need to basically give on the once chip is manufactured on a silicon bring up, or basically because let's say you can say tie testing or package level testing. You have to give that pattern, and you need to make sure that you are getting the proper response. So what is proper response? I hope I answered that question. Is it like uh, Hello.
It's okay. Okay.
Yeah. I mean, it is no specific thing. Each fault model is important, and each one has a certain priority. Like first we need to run this one, and then next one, and then the next fault model. So we have to basically analyze each and one, and you need to find out the particular defect. Okay. Now, as I mentioned here, like expected response here. Okay. So what is expected response here? Let's say I gave 1 1. My expected response is basically 1. This is my expected response. So when I'm generating that particular pattern here, right? Okay. So I'll be giving 1. I'll be saving that expected response also for this AND gate here. Okay. So let's say this particular node is stuck at 0. So on AT, let's say this particular one chip is manufactured, right? And this particular node is stuck at 0. If I give 1 1 pattern, I'll be getting 0. That means this particular chip will fail because it will compare with the expected response. Yeah, I'll be getting 0, but expected is 1. So this is how we find out, okay, whether it's a good die or bad die. I'm giving very basic thing, but in real scenario, there are multiple patterns and different kind of combinations and different kind of fault model, as I mentioned, right? Stuck at transition and all. Okay. Okay, part D. Okay, sir, any other question before going to the next fault?
I think there is no question right now.
Okay, okay. Now, you might have yesterday, right? Leakage current, I think, right? There is static current, dynamic and static current, right? So even though your chip is in off state, but still some leakage is happening, right? So how basically with the help of this IDDQ, right? Now, let's say for example, this is your inverter right here. This is VDD, and this is ground here, right? So you are giving 1, you are getting, you are expecting 0 here, right? This is your normal operation. But let's consider this is like these are different kind of bridging faults, okay? Or there is a mm, uh, during manufacturing, right? This is properly not properly the thin wiring, right? Or there's a bridging fault, right? IDVQ is basically the we call it the question current. So let's say we have issue at this particular region here, okay? So because this one it will go here, right? This one will not go here. So suddenly this all this current will flow like this, okay? Okay, so this is kind of one leakage kind of scenario will happen, okay, suddenly. And this is not just one, right? Let's say this is one inverter as is, I have drawn here, right? Now we have, you can see we have billions of transistors, right? So we let's say most of the logics, right, in this region of the chip, in this region of the chips, right? Okay, so everywhere we have this kind of issues here, right? This leakage issue. So you are basically sudden, you can see I just mentioned here, right? So this short defects, right? Or maybe you can say the defect, or maybe you can consider this short here, right? So this will basically cause a massive current spike. Okay, so this leakage will happen, so it will impact on your battery and all, right? So now the functionally, as again, I'll be basically mentioning functional and DFT between, right? So this are like functionally there are no certain test cases, okay, to find out this kind of faults. This is where DFT basically find out that particular fault and basically will try to analyze it or try to fix it, that particular faults, or we can just give the region, okay, this in this region there is a failure, we and our patterns will pinpoint where exactly the issue. Okay, let's say this inverter level is the input, there's a fault defect is there, okay. And as I mentioned, there are different techniques to find out the or fix the faults. So that particular team is basically get that information and they will try to fix that, okay. So this is how basically we can basically cover that, or basically try to find the faults which is to leakage. And uh, and you can see this excellent for reliability, early life failure. Now you can see your battery also, right, in your iPhone and all, right? You are the percentage here. So slowly after 1 or 2 years, right, you are seeing that percentage is getting reduced here. That means your transistor, right, that transistor is not working properly because already 2 years, right? So uh, you can call it the aging, right? This aging is happening. Okay, so there are kind of aging failures are also there. Okay, so these are very important here. And how will you find out that aging related failures also? Because so I have manufactured chips. I don't know what will happen after 5 years, whether this chip will work or not, right? So there are different kind of ways also. There's aging simulations. Okay, so that is very mandatory for each or critical chips, let's say automotive, and then mobile also. I mean, everywhere it is mobile, like you can see, right? In 1 or 2 years, basically, people usually change the mobiles, right? So it is only in the certain features, let's say in your modems and all, in the processor only, we have that aging related checks. Okay, but in automobile and all, right? Because people buy the car, they use for 5 6 years or maybe 7 8 years, right? So this is where that aging uh, related failures will comes in picture. Okay, so slowly the transistors and all, they will degrade, the performance will degrade, and that kind of then they're kind of different kind of, let's say, if you're using is there a certain, let's say, if you if you are that particular, there's a you can say there are different kind of, let's say, temperature. Okay, there's a pressure, right? And voltage, right? Suddenly there's a big like you'll be seeing, like all your, let's say, there's a huge current is incoming current, right, which will destroy your all these electronic gadgets here, right? So there are different kind of basically process variations, temperature, basically, as I mentioned, right? The pressure, voltage, and all. So that will impact on the your all the electronic gadgets. Okay, and eventually your particular all these transistors, basically they will degrade, your performance will degrade, your mobile will get hang and all, or maybe any electronic device will get hang because of this one. So now that's why this aging related checks are also very important. Okay, I'll cover that also, but I'm just because of this leakage also, it is kind of like early life failure, right? We can basically identify this kind of issues, right? Let's say this very small uh, defect. Okay, let's say eventually the thin wiring is there. Okay, suddenly now it is working, but after, let's say, 1 or 2 years, this will get basically degrade, and then it will impact on the short or maybe open, right? Now let's say there is no connection here from this to this here. Okay, this particular leg to this particular, there is no then this is where that fault will come in picture. And most of the let's say inverters, right, in this one, let's say they have this kind of uh, open faults. Okay, and this is where then that huge leakage will come. You'll be seeing your mobile batteries getting discharged very quickly, right? All these basically are basically pinpoint to this kind of faults here. Okay, so now we have aging related checks. There are different techniques. We run for 200 hours, which will be equivalent to, let's say, 5 years 6 years kind of uh, usage. Okay, on certain dies once we manufacture, and uh, basically we kind of correlate. Okay, and after that again we'll test that that particular die, and we'll make sure that that die works properly. If there is any failure, then we need to identify what kind of failure is there. Then we need to, as I mentioned, there's a thin wiring and all, right? So we have to basically fix that particular die here. So this is how we can basically uh, find out the early life failure here. Okay.
Hello, Sagar. How
Yes.
many more slides? How much time?
This is again different. I just give an example here. Let's say if you run 200 hours, right, it is considered to around 5 6 years kind of usage.
Mhm.
Okay, it is depends. It depends on the application of chip, automobile, and then let's say in space, the chips used in the satellites and all, right. Each will have the different criteria, and each will have a different kind of the hourly or aging related. Basically, we call it aging simulations. Okay, so those basically we have to analyze. There are certain rules are there with respect to that we basically analyze that hour to years ratio. Yeah. Okay, and all these faults
Yeah.
basically, right, that will now let's say you ran for 200 hours, that is equivalent to 5 6 years. You ran that particular chips, and then you found out, oh, okay, now let's say, as I mentioned, 200 hours means what? In 200 hours, this particular will get open here. Okay, and your chip will give the huge leakage current here. So this is how we find out what will happen after 5-6 years. I hope you got it right, ma'am. Or
Yeah,
do you have any
yeah.
follow-up? Yeah. Okay. Great. Okay. Any questions on this one? Leakage current or identity current? Okay. I'll go to the next one. Next one is the scan architecture. I think I have covered the fault models and
Yeah.
okay. So again,
How
the
much
same
more
diagram.
time you'll take?
Okay. I covered only 50%.
Yeah, because it's already 9:10. At 30 we had to complete.
Okay, I'll be covering that a few slides, 2 to 3 slides, and then we
Yeah,
can.
yeah.
Yeah, you can
Yeah,
just let me know. Then
it's
we will stop.
no, no,
Okay. Yeah.
it's more interesting because it's still
Yeah.
141 participants are there who want to hear,
Yes.
but
Yes.
then to
Yeah. Yeah.
like let them know. Yeah.
Yes, yes, sure, sure. Now, okay, yeah, quickly we'll cover. Now we'll go a little fast now. Now, as you can see, now let's say now this is your particular normal D flip flop here. Okay. Now this is where now what is a scan flop, what is a normal flop, right? Our D flop is basically D, Q, and clock, right? And some flop will have set and reset that I'll mean I'm not going to mention now. Just consider we have D, clock, and Q here. Okay. This is your functional flop here. Okay. Now this particular leg is going to, let's say, AND gate. Okay. Again, this particular is coming from another flop here. Okay. This again D, this again Q, right? And this output of this again going to another T here. Okay. And this is, let's say, this is going to the output here. And this is my, let's say, input here. Okay. And this is again another one. This is second input here. Okay. Now, this is your normal, let's say, functional logic here. Okay. Now, with respect to, we have to convert that functional logic into the scan logic here. So how will you do that? We'll just add one mux here for every flop. Okay. And this is the 0 leg. This is the 1 leg will be my scan in here. And my select will be scan enable. Okay. We call it the scan inputs, scan enable. And basically in some companies, they use the functional queue only, or they'll have a different leg here. Basically they call it the scan output here. Okay, but yeah, we can consider this side queue is my scan path here. Okay, now I have converted that flop into the scan flop. Now this is my scan flop. Entire thing is my scan flop here. Okay, and all this scan enable is basically same as this one. Same scan enable we are routing to each flop mux select here. Okay, and this si, right? Now this is, I have converted to the scan flop. I know drawing is a little bad here, but yeah, you please understand or kind of correlate. Okay. Now next is basically I need to stitch it. Okay. Stitch it means was I'll see this is my functional path. Now I'll be connecting this queue to next SI here. So this is this one. This one is my first flop. You can consider. You can. So this is my first flop. This one is my second. So in this diagram, this is my second, and in this diagram, this is my third. Okay, this is again my third flop. Okay, so you can see the first flop queue I have connected. You can see this particular. I'll take the new different color. So this queue, right? I'm connecting to the mux of the. I mean ESI of the that particular mux or this particular flop here. Okay. Again, output of Q, right? It is going to the functional logics. Okay, and again it is going to the next flop here, this one. Okay, Q also. So this is how I have created one scan chain here. Okay, so this we call it the scan chain here. Okay, this kind of scan chains will have n number of scan chains. So in my design, right? Okay, I'll take the different color. Okay, so in my design, I'll have n number of scan chains here. Okay, this is my scan input. This is my scan out. Again, I'll have, let's say, two different yes I yes so. Okay, this is 0, this is 1, this is 0, this is 1. So I have basically two scan chains here. Okay, so what I'll be doing, I'll be basically shifting the data from this SI, and at the end in, let's say, three three, let's say the scan chain length, right? Length means how many flops are in that particular chain here. Okay, let's say in both the chains I have 3 flops, so my scan chain length, I'll be using some short form. Scan chain length is 3 here. Okay, so in 3 cycles, I'll be, let's say, giving, as a in earlier example also I took 3 cycles only. So this particular patterns I will basically shift in. Okay, and that pattern basically will go to this all this combinational logics. Okay, and sorry. Yeah.
Parkai sir, please can you mute yourself?
Sorry.
Yeah. Okay. So in each in shift in will load the data. It will go to this AND gate. Output AND gate will come to in the capture window. It will come to next D, and that D will capture the data in the capture window. And in the next, again, now I need to give that as in earlier example also, I need to give some other I need to control other nodes. I'll be giving 0 and 1. Okay, so this I will shift in, but whatever the value that I have captured in that particular window, right, that will get shipped out, and we can observe that scan output 0 and scan output 1 here. Okay, now this is one this is scan teaching, and this is the scan operation here. Okay, this is again the serial access. I will not cover this one. So as I mentioned, the shift in will load 101. That shift in, let's say in 3 cycle, that data will get shipped. Okay, and it will go to the AND gate, and this is my capture window. Will give only one pulse here in the capture window. And let's say this is we are doing stuck at fault testing. Okay, I'll give ESA stuck at fault. Okay, so in this one we'll just give only one cycle. This also region we call as a different naming, but I know time here with time limit. We call it a launch and capture. Oh, what happens? Oh, sorry, I'll just try it again. Okay, so this is my capture window, and again I'll be shifting out that data in the next cycle. So what happens, right? So 101, I'll shift in this one. Okay, that value will get captured, launch and capture in this one, and whatever the value that I observe at the flop output, right, it will get shipped out at this one. But again, next data also will get shipped in. Okay, so we'll have shipped out plus shipped in. Okay, in this one. So all these upcoming cycles, right, based on the how many nodes that we're controlling, those many cycles, those many operations will be there. Shift in, this operation will repeat. Okay, shift in, capture, shift out, then again from the next one, shift in, capture, shift out. So it is like basically like this: shift in, capture, then again like this. Okay, so till let's say we are covering let's say in this case 1 2 3 4 5 6, right? We have 6 node in the design, so these many times that operation will happen. Okay, and at the end we'll be covering entire nodes, so we'll be getting 100% test coverage here. Okay, so we have covered all the nodes in the design, so that once the chip is manufactured, I'll be giving all these different kind of patterns. Okay, this let's say this is 100 111 011, like this, all these patterns, right? I'll be giving once the chip is manufactured, and I can check whether that is there any stuck at 0 or stuck at 1 fault. So same things apply to the ASPIT also. So there also we'll be covering entire node, will generate the all the patterns, will go through this sequence: shift in, capture, shift out. Okay, and we can basically generate those patterns, and we can on the once the chip is manufactured, we can basically test those. Okay, and as I mentioned, the scan enable, right? We can basically globally we are routing that scan enable to the all the mux select here. Okay, so you can see requires dedicated high fan-out buffering here. Okay, so there are different kind of buffer also. Yesterday I think sir has mentioned, right? So to create a buffer also, right, we have to use basically very high performance buffering also. Okay, so high performance buffering means that we have to that all this current and all everything will come in picture here. Okay, so there are different kind of buffers we have to use on that part, so that what happens, right? So in this window, right, so in this window your scan enable is 1, in this window your scan enable is 0. Okay, so that means whatever the value came from that AND gate, right? Okay, that D will basically will capture at this edge, will launch on this edge, capture on this particular edge. Okay, and in this window when scan enable is 0. But again, as I mentioned, it is like I just draw it here, like let's say that the sharp 1 to 0. But in real scenario, it will basically go like this. Okay, so in you can see, let's say this is my design. Okay, and this is my scan enable here. Okay, and this scan enable is going all the way to this particular flop here. Okay, so and it is, let's say it is going to this particular flop also. Okay, so you can see by looking at this is by looking at this only, right? You can see the delay will be more for this path than this one. Okay, so you need to make sure that you are putting very high performance or you're using high performance buffer and all. You have to delete this little bit also, so that you need to make sure that the scan enable is basically going to 0 in that particular window only. Okay, and becoming 1 only. Okay, so that's how we have to cover that scan enable, and then you capture this particular window, right? This capture one. This will basically get that data from the first shift in, and then we can observe that. Okay, on the output. Okay, so that's why this global scannable, there are different techniques also. Now every instead of routing, let's say in earlier I gave one example, this 4 1 2 3 4. Okay, now let's say from the top level I have only one scannable. There are different ways also we can generate internal scannable by with the help of this one. So I'll have to basically route this scannable to only that particular logic here. Okay, not to the all fault, all the flops. Okay, so this internal logics will basically generate the new scan enable. Okay, this new scan enable, and that scan enable will cover only this core flops here. This scan enable will cover this particular flops here. So this is how we need to basically you can say this one kind of methodology or kind of DFT improvement or routing, right? That because as I mentioned, right, the route place and route basically physical design basically uh, they do all that place and route, right? So if they see this scan enable is basically routed to each and every flop, right? So they will see a lot of congestion here, right? Because this scan enable is routed to every flop, lot of congestion, and it's very difficult to place and route, right? So this is how we need to come up with different kind of solution to make sure that we are reducing routing so that it will be easy for the PD for the place and route. Okay, we need to have some space also, right? I mean, there's a wires and all. I'll not go into the details, but yeah, overall you can see we have to come up with certain solution to make sure that there's a because DFT logic there should not be congestion. So we have to use different approach to make sure that routing is uh, uh, routing congestion is very less here. Okay, this is one important thing I'll just cover in the expert testing here. So we have called on-chip clock control. We call it OCC here. That OCC will basically cover the fast clock. Fast clock is basically a functional clock. As I mentioned earlier, we have like let's say 1000 megahertz, and this is my slow clock here. Okay, and this slow output of this one is going to that particular flop clock here. Okay, CLK here. Okay, so in the stacked testing, right, we are using the slow one, slow clock. Okay, because we don't have to cover that slow to rise and slow to fault here. Okay, why we do not have to cover that particular path? Because we know it is like stuck at 0, stuck at 1. Either because AND gate it is, let's say one leg is, let's say, ground to 0, it will be always 0. I don't have to worry about whether it is slow to rise or slow to false here. So I can basically work with the slow frequency. And another challenge is here timing closure also. Okay, so to cover on that with respect to only for the scan path, right, to cover the to basically make sure the timing closure is proper for the scan paths. So that is also very difficult if we use a very high frequency. Always it is better, like let's say if you use as much as high frequency, your test time will be less. Yeah, but there are certain challenges here. Okay, now in the as I mentioned in this one, let's say in this scenario, I am using this capture window, same clock here. Okay, this slow clock I'll be using for the stacked testing. Okay, but for at speed for transition, I'll be using TDF, transition delay faults. So I'm using for shifting purpose, I am using slow clock here. Okay, the same slow clock. But in the capture window, okay, in the capture window, I'm using basically functional clock, this leg here. So this is here, this OCC basically on-chip clock control, right? This will, so this clock is a free running clock, okay? This will always pulse, but I don't want to give all the pulses, okay? I don't want to use all the pulse. What will happen if we use the entire thing, okay? Again, you know, right? The dynamic power, right? It is directly proportional to the frequency, right? Here, if you use as many as cycles, or if you do not have proper gating or clock gating cell, right? You can consider OCC as a clock gating cell, okay? Whenever we need that time only, we'll enable that particular clock, and we'll basically give the pulses out of it, okay? So in this window only, we'll enable that enable of that on-chip clock control, and only these two pulses only will give it, okay? Because less 100 megahertz, it is directly proportional to frequency, your power dissipation will be very high, right? So this you can relate to your basics here, okay? uh, yeah, so you can see we have different faults, and in the capture window we are using different clocks. As I mentioned, we have different why we are using that also, okay? Because we need to basically check with this, because functionally, right, this flop to this flop here, right, D to Q here, okay? This is D, this is D, this is Q, and in this Q. Functionally also they'll be running at let's say 1000 megahertz, okay? But they don't have test case to cover that this path here, whether it's a there's a transition delay faults, or any kind of path delay faults here, okay? So this particular fault testing will make sure that there is no transition delay faults, and then the functional features will work properly, or functional chip functionality will be proper, okay? uh, I think there are certain few more slides. I think boundary scan I'll not cover, or maybe just quickly I'll give. So this is my entire chip here. All this I have certain inputs here. Okay. Now the thing is, let's say functionally, right? Let's say you have issue at this particular port only. Okay. So whatever the input that you are giving, that itself has some issues, right? So there is no use, right? Even if you give one, it will not go to actual your core logic here, right? It will not go to your actual chip functionality here, right? So we are using the boundary scan tab, okay, or JTAG, right? We are using that already, that standard or IP tab IP, and with the help of all this TDI, TMS, TCK, right? We are basically there are certain uh, methods like bypass, then X test, in test. There are different kind of testers are there. We use those test cases, and we make sure that what all these pads are basically working properly. Okay, from the pad, then only that all this what are the data that we're giving to the internal logics, that will go to the this one, and we can then cover the next faults. Okay, your boundary scan itself is failing, that means you have no faults. You will not be able to check those stack at fault and all, right? You need to make sure that boundary scan works properly. Okay, so as I mentioned, each test is dependent on each other. Okay, so boundary scan is very high priority. Every company, based on the chip size and all that, very small chips, because again, to add that particular logics and all that, it will again some area overhead, right? So for small chips and all, very limited IOs. Okay, so let's say for fingerprint sensor, and or let's say your power management IC, right? They are very small in size. Okay, for such IPs there is no boundary scan, or this one. Okay, because they have certain different ways to test that, and because due to limited number of one or two IO, five IOs, like, okay. So there is no IO, but in big chips, like let's say we have 5,000, 10,000 scan IOs, right? So in that way, we need to basically make sure that we have boundary scan, and we can cover that all the pad functionality. We need to make sure that pad is working properly, and then only our other fault testing, or other functional tests is also verification also, right? That will also uh, uh, pass, or we need to check on that. Okay, so tab control, I will not go over this all the tab, shift
Hello.
IR, DR and all. Yes.
Sagir, we
Yeah.
are really short of time because we have to
Yeah.
end at 9,
Okay.
9
Yeah,
p.m.
sure.
So we extended
Yeah.
for 1 hour.
Sure. Yeah, no problem. I think I have covered most of the basic things. If you have any questions, you can reach out to me through LinkedIn, or you can take my contact number. I'll be happy to take any session anywhere, anytime. Just let me know, just 10 to
Is
15 days.
is there any open source softwares that are available for testing and fault finding purpose to
No,
students
it is
and faculty
that's
members?
why no this all okay. Every college, right? They can basically so each EDA companies, right? Let's say I mentioned Mentor Graphics, Synopsys, or Cadence, right? They give some free tools to colleges. Okay,
Okay.
it is I think college I think can reach out to these companies. Okay, you can just send a mail to them. Those guys can give you some free softwares, and I think you can use that for this DFT related tools, right? You can use for the your project purpose and all. Okay, all these IITs and all, right? They already have their as I mentioned, right? Uh, they already got some this they buy it also. They have some free tools also. So it is depends. Like sometimes if you have like really high requirement for the project purpose and all, right? They basically give for some 1 month or 2 months kind of in that period. Okay, so you can reach out to the
If
those
you have
companies.
any such a free resources, so please give information to us. Okay, so we
Yeah.
will share with the
So for
participants.
yes, sure, sure. Because these are, as I mentioned, right, this DFT is very important part, right, integral part, and this is where the cost is basically uh, importance, right? Because let's say if you are basically manufacturing 1,000 chips, let's say 100 chips are bad. How will you find out, right? This 100. So this
Right.
is where cost is very important here, and test time is also very important here. Okay, so most of the uh, entire chip cost, right, it depends on the DFT verification. Okay, so it is very difficult to get those tools because they are already limited and this one, but they will give for sure. They give to the universities, colleges, and all. So you surely just send a mail. They'll get back to you. Their entire team will come if they approve. Their entire team will come and they will basically install. They will give the demo on that front. Okay.
Okay.
So on this note, I'll just stop sharing. And yeah, as I mentioned, you can reach out to me on LinkedIn or you can take my contact. I'll take some session, extra session if you want. But just let me know just 15 to 20 days before so that I can plan that.
Thank you, Sagar, for your wonderful
Yeah,
session.
yeah,
Now I invite again Doshi ma'am to express the vote of thanks.
yeah.
Yeah, sure.
Ma'am?
Am I audible?
Yeah,
Yes,
yeah.
ma'am.
Yes, yes. Okay. Really, it was a great session, was Sagar, but we couldn't do
Yeah,
justice to the knowledge you were sharing
yeah.
because we were running
Yes,
out of time.
yeah, yeah.
But
Sure,
surely we will see that we will arrange one more session in
sure.
which the interested candidates can enroll, and we will
Hmm.
continue with that.
Sure, sure,
Okay,
sure, ma'am.
so with
Yeah,
this, I, on behalf of SVPM, would like to extend our heartfelt guidance to
yeah.
you to the for this today's ATAL faculty development program. Really,
Yeah.
your deep expertise as well as expert
Hmm.
senior DFT engineer, coupled with the role as a technical lead and Silicon innovation specialist, made this session truly impactful.
Yeah.
The clarity with which you connected the complex industry practices to academic
Hmm.
learning was both inspiring and empowering for the participants because we are from the
Yes,
academic field. And
yes,
because you have the practical experience, it was
yes,
really difficult for us, but then you related it and made the complex industry problems very simple. So,
yes.
beyond technical knowledge, your passion for innovation and mentorship
Hmm.
deeply
Yeah.
resonated with the faculty and
Yes,
researchers. So, again,
yes.
on behalf of the organizing team, we sincerely thank you for
Yeah.
generously sharing your time, experience,
Hmm.
and vision with us. Hope we'll
Yes,
connect back again. And
sure.
thank you once again for accepting and sharing your expertise with us.
Yeah,
So, thank you
yeah.
once again.
Yeah, thanks a lot everyone for listening to me for this 1.5 hour.
No, no,
Okay.
no, no. It was really
Yeah, I
amazing.
hope I hope
Uh,
you enjoyed that session.
Uh,
yeah, yeah, yeah.
Yes,
We
I
yes,
were
really
enjoying like,
appreciate the patience of the participants also because it's
yeah,
the
yes, yes.
9:30
Yeah,
and
because the way you
yeah,
they are
made to
attending.
me simplified the things was commendable. Like, so it's really
yes,
commendable. It was.
yeah,
So I feel
yeah.
we will have one more session, especially for
Sure,
VLSI
sure.
guys.
Yeah, because you will not get
So it was really
where
wonderful.
DFT related, right? It is very
Yeah,
even
no,
on
you don't have any
even on internet.
literature.
Yes, yes, it is
Yeah.
very difficult. Yeah, because easily people do not share. I mean, there are some institute also, but still it is
Yeah.
very basic. And yeah, I think once you understand basic, then only you will be able to understand what are the challenges and all, right? So yeah, so certainly I think thanks a lot for this opportunity. I think you requested me a long time back, but sorry, I didn't get time
No,
before.
no, no. But then
Yeah,
you found correctly at the time
yes,
of
yes,
faculties, like because
yes,
totally there were 200 participants who were listening
yeah,
to you.
yeah, yeah.
So it
Okay,
was really essential
yes,
for
yes.
some industry experts to come and give the awareness to the technical,
Mm-hmm,
academical faculty members.
mm-hmm,
And the knowledge, I told you, ki it is not
mm-hmm.
available anywhere. So
Yes,
it
yes,
was your
yes.
experience which you are sharing.
Mm-hmm,
But then
mm-hmm.
because of some short of time, but next
Yeah,
time we will see that
sure,
you will
sure.
get enough time, and even
Yeah,
we will get enough time
mm,
to
yeah,
interact with you.
sure, sure. Maybe I will have some festival session also, because explaining on the
Yeah.
board it is very easy and people can correlate. Okay.
Yeah, yeah.
Yeah, 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 sure,
Mm.
sure. Okay, yeah. Thanks
Thank you
everyone.
once again.
Thank you,
And
thank you.
again, really hats off and proud of
Yeah,
you. Thank
yeah.
you.
Thanks a lot. Yeah, thank you.
Thank you, Sagar. Thank you.
Yeah, yeah. Bye, bye, everyone.
Bye.
We are ending the session now.